Good evening and welcome to Physic for Sleep. Tonight we embark on an intellectual journey exploring the intriguing question of how big is the universe really, delving into the fascinating donut universe theory. Before we gently immerse ourselves in the boundless cosmos, I would like to know where you are at this moment. Perhaps you are nestled in a window seat on a quiet night train, watching the blurred lights of distant towns pass by. Or maybe you are gazing up at the vast, silent sky from a secluded balcony, the stars just beginning to emerge. If these deep reflections help you relax and organize your thoughts before sleep, please support the channel with a like and subscribe so others can find their way here too. Now, just breathe. Allow your eyes to grow heavy, and let's begin. We often gaze into the night sky, captivated by the countless stars and distant galaxies, and instinctively wonder about the sheer scale of it all. How far does it truly extend? Our immediate perception is limited to what we call the observable universe, a vast sphere with a radius of approximately 46.5 billion light-years. This isn't a physical boundary to the cosmos itself, but rather the limit of how far light has had time to travel to us since the Big Bang, which occurred roughly 13.8 billion years ago. Since the universe is expanding at an accelerating rate, the objects that emitted that ancient light are now much farther away than 13.8 billion light-years, giving us this immense observable horizon. Beyond this cosmic frontier, space undoubtedly stretches further, carrying with it countless other galaxies and structures whose light simply hasn't reached our telescopes yet, and perhaps never will. So, the universe is certainly larger than what we can currently observe, but the profound question remains: is it truly infinite, or does it eventually loop back on itself in some grand, unimaginable way, perhaps like a cosmic ring? Cosmologists, guided by the intricate dance of mathematics and the subtle whispers from the early universe, have long contemplated its fundamental geometry. When we speak of the universe's shape, we're not talking about a form that exists within a larger external space, but rather the intrinsic curvature of space-time itself, how it bends and warps. Imagine for a moment the surface of a two-dimensional object. A flat sheet of paper represents a zero-curvature space. The surface of a sphere possesses positive curvature, where parallel lines, if extended far enough, would eventually converge, like lines of longitude meeting at the poles. Conversely, a saddle-shaped surface exhibits negative curvature, causing parallel lines to diverge, spreading ever further apart. Now, elevate this conceptualization to 3 dimensions. An open universe would possess negative curvature, endlessly sprawling outwards like an infinitely vast cosmic saddle, its volume forever increasing. A closed universe would exhibit positive curvature, forming a finite, self-contained realm, much like the surface of a 4-dimensional sphere, where a journey in any direction would eventually bring you back to your origin, without ever encountering a physical edge. Lastly, a flat universe with zero overall curvature would extend infinitely, a boundless Euclidean expanse where parallel lines remain parallel. Current observations, particularly from meticulous analyses of the cosmic microwave background radiation, the faint afterglow of the Big Bang, suggest that our universe is remarkably flat on large scales. This flatness is intimately determined by the universe's total density of matter and energy compared to a critical density. If the actual density precisely matches this critical value, the universe is geometrically flat. Data from groundbreaking missions like the Wilkinson Microwave Anisotropy Probe, or WMAP, and more recently the Planck satellite, have measured these subtle temperature fluctuations in the cosmic microwave background with unprecedented precision, indicating that the universe's geometry deviates from perfect flatness by no more than about 0.4%. Such an astonishingly precise measurement strongly supports the flat universe model. This observational flatness often implies an infinite universe, a concept that can feel both liberating in its sheer, unbounded vastness and overwhelming in its lack of discernible limits. a seemingly endless ocean of galaxies. However, even a universe that appears flat locally, or on the scales we can currently observe, could, on a truly immense scale, possess a more complex global topology. This brings us to one of the most intriguing and mind-bending propositions in modern cosmology, the idea of a donut universe, or more technically, a toroidal universe. Imagine a three-dimensional space that, instead of simply extending indefinitely in all directions, has its opposite sides topologically identified, effectively wrapping around on itself. This means that if you were to travel in a perfectly straight line through such a universe, you would, after an incredibly long voyage, eventually return to your starting point without ever encountering a physical edge or a conceptual wall. You would have traversed a cosmic loop, not by physically curving your path, but by moving through a space whose distant regions are intrinsically connected to nearby ones, like an explorer circumnavigating a planet. This isn't merely a playful thought experiment, it's a serious geometrical model, often referred to as a multi-connected universe. In such a scenario, the universe would be finite in volume, yet it would possess no discernible boundaries. To visualize this, consider a two-dimensional analogy. If you take a flat sheet of paper and connect its top edge to its bottom edge, you form a cylinder. Then, if you connect the remaining two circular edges of the cylinder, you create a torus, or a donut shape. An ant walking on the surface of this torus would never find an edge. It would simply keep moving and eventually return to its starting point, having effectively looped around. Now extend this idea to three spatial dimensions. Our three-dimensional space could be similarly wrapped around on itself in 1, 2, or even 3 independent directions, forming what physicists call a three-torus. Crucially, a three-torus can have zero intrinsic curvature, meaning it appears perfectly flat to local measurements, perfectly consistent with our precise CMB observations, yet it remains finite in its total extent. The implications of a toroidal topology are profound and offer fascinating possibilities for understanding the cosmos. If the universe were indeed shaped like a donut, then light traveling from distant galaxies might loop around, allowing us to see the same galaxy or even the same cosmic structures from different angles and at different points in their evolutionary history. It would be like looking into a cosmic hall of mirrors where the same celestial objects appear multiple times across the sky, albeit at varying stages of their development due to the immense travel time of light, each image a ghostly echo of the past. This phenomenon is sometimes referred to as cosmic crystallography, where astronomers would search for repeating patterns or circles in the sky within the cosmic microwave background or the large-scale distribution of galaxies. Detecting such subtle, repeating patterns would provide direct empirical evidence of a finite, multi-connected universe. Scientists meticulously analyze these intricate patterns in the cosmic microwave background, searching for faint, repeating echoes of the universe's earliest moments, which could serve as a cosmic fingerprint of such a topology. For example, if the universe were smaller than the observable horizon in certain directions, we might expect to see matching circles of temperature fluctuations in the CMB, where the light from the same region of space has looped around and reached us from opposite directions, creating identical patterns on different parts of the sky. While early tantalizing hints were explored, subsequent more precise data from the Planck satellite have placed strong constraints on these possibilities, suggesting that if such a toroidal topology exists, its wraparound scale must be larger than our observable universe. This means that any cosmic loops are currently beyond the reach of our direct observation, making detection incredibly challenging with present technology, and leaving the ultimate global shape a magnificent mystery. Nevertheless, the contemplation of such a universe invites us to rethink our place within the cosmos. If the universe is finite but unbounded, a grand, intricate loop, it implies a certain self-contained elegance, a cosmic symmetry. We are not merely lost in an infinite, perhaps intimidating void, but rather part of a beautifully interwoven tapestry, where every point is, in a profound sense, connected to every other. This geometrical possibility transforms the abstract concept of cosmic scale into a more intimate, cyclical journey, allowing us to ponder not just how vast our universe is, but how intimately connected its vastness might truly be. Consider the quiet solitude of your own existence, surrounded by the cosmic expanse. In a toroidal universe, the most distant light you perceive could, in a profound and almost mystical way, be a reflection of light that originated from a region topologically close to your own, having simply traveled the long way around. It offers a sense of ultimate connection, a cosmic embrace where the very fabric of reality gently folds back upon itself, ensuring that nothing is truly ever lost to infinite separation. This endless yet contained dance of space provides a tranquil backdrop for our own fleeting moments, a comforting thought as the vastness of space cradles you towards sleep, reminding you that you are part of an elegant, self-referential design. We ended our last reflection by considering the profound elegance of a universe that might be finite, yet utterly without boundaries, a self-referential design where the most distant light could be an echo of regions topologically closer to our own. This concept, while initially counterintuitive, emerges from a deeper contemplation of space-time itself, extending beyond our immediate perceptions of scale and linearity. The very act of questioning the universe's global shape compels us to consider the foundational principles that govern its existence. Why would the cosmos adopt such an intricate, folded geometry? The answer often lies not just in observation, but in the elegant whispers of theoretical physics, where certain models find a natural home in such topologies. One of the driving forces behind exploring these multi-connected spaces is the desire for a universe that is, in some sense, complete or closed, without resorting to an infinite expanse. While the observable universe appears flat, this is merely a local measurement, akin to standing on a vast, seemingly flat plane, and concluding the Earth itself is flat. For millennia, humanity has grappled with the idea of infinity, often finding it conceptually challenging, even paradoxical. A finite yet unbounded universe provides a compelling alternative, offering a cosmos that is self-contained and perhaps more aesthetically pleasing to some theoretical frameworks. Such a universe could be closed in a topological sense, meaning it has a finite volume, even if its intrinsic curvature is precisely zero. This is a subtle but crucial distinction. A truly infinite flat universe would have an unbounded volume, stretching forever. A flat toroidal universe, however, would have a finite volume, despite exhibiting no local curvature. Consider the early universe, specifically the epoch of cosmic inflation. This widely accepted theory posits that in the immediate aftermath of the Big Bang, space-time underwent an exponential expansion, smoothing out initial irregularities and leading to the observed uniformity and flatness of the cosmic microwave background. While inflation generally predicts a universe that is either flat and infinite or very nearly flat and very, very large, it doesn't strictly rule out a finite, multi-connected topology. In fact, some inflationary models can naturally lead to universes with such non-trivial global shapes. The immense stretching during inflation could have taken a small, initially compact space and expanded it to colossal dimensions while preserving its underlying connectivity. Imagine a tiny fabric of space-time, perhaps intrinsically folded from the very beginning, then stretched to an unimaginable size by inflation. The local appearance would be flat, but the global structure would retain its original, intricate folding. The challenge, then, lies in detecting these subtle topological imprints. If the wraparound scale of a toroidal universe, often referred to as its characteristic length, is significantly larger than the diameter of our observable universe, then we might never be able to directly observe these cosmic echoes. The light from a distant galaxy would take longer than the age of the universe to complete a full loop and return to us, or even to reach a point where its other side becomes visible. This means that while the universe might be finite, its boundaries, or rather its self-connections, could remain forever beyond our observational horizon, rendering it effectively infinite for all practical purposes of exploration. This profound limitation reminds us that what we observe is not necessarily the entirety of reality, but merely the portion that has interacted with us over cosmic time. Our current cosmological models, while incredibly successful, are ultimately based on data from within our observable bubble. Yet, the search continues. Scientists employ sophisticated mathematical techniques and algorithms to scan the cosmic microwave background data for any telltale circles in the sky, matching temperature fluctuations that would indicate a smaller, multi-connected universe. These analyses look for correlations in the CMB on angular scales larger than those that could be explained by random fluctuations in a simply connected, infinite universe. So far, the evidence strongly points towards a universe with a very large, if not infinite, characteristic length, pushing any potential toroidal wraparound beyond the limits of current detection. This doesn't entirely rule out a donut-shaped universe, but it does imply that if it exists, it is far grander in its self-connection than we can presently perceive. The concept of a finite, unbounded universe profoundly influences our understanding of cosmic horizons. In an infinite universe, every observer effectively has their own observable horizon, a bubble of light that expands with time. But in a multi-connected universe, the concept of a multi-connected universe, finite yet without boundaries, subtly reshapes our understanding of cosmic horizons, moving beyond the simple notion of an ever-expanding bubble of observability. While the direct detection of these cosmic connections remains a profound challenge for our current instruments, the very contemplation of such a topology deepens our appreciation for the intricate fabric of space-time itself. We are accustomed to a linear progression, a continuous unfolding of events and distances. But a toroidal universe suggests a more cyclical, perhaps even self-referential reality. It asks us to consider whether the vastness we perceive is truly endless, or if it gently folds back upon itself, creating a cosmic tapestry where every thread eventually reconnects. In a universe with a toroidal topology, the light from a distant galaxy might not simply travel in a straight line forever. Instead, if the characteristic length of the universe is sufficiently small, that light could eventually loop around, returning to its point of origin, or even appearing to us as a duplicate image of the same galaxy from a different perspective. This phenomenon, often termed a cosmic mirage or ghost image, would mean that when we gaze at a particular cluster of stars far across the sky, we might in fact be observing the very same cluster that exists in another direction of the looped cosmos, albeit at an earlier stage of its evolution. The time it takes for light to complete such a loop could be billions of years, making these repeated observations appear as distinct celestial entities. Such a discovery would fundamentally alter our perception of cosmic uniqueness and the sheer number of galaxies that populate the universe. The search for these cosmic echoes is an active area of research, primarily focusing on the cosmic microwave background. The CMB, being the oldest light in the universe, offers a pristine snapshot of the early cosmos, before the formation of stars and galaxies. If the universe were indeed multi-connected on a scale smaller than our observable horizon, then the patterns of temperature fluctuations in the CMB should exhibit repeating features or large-scale correlations. Imagine the universe as a vast, echoing chamber, where the primordial sound waves from the Big Bang reverberate and leave identifiable imprints. Scientists search for these specific patterns, such as matching circles of hot and cold spots across the sky, which would signify that light from the same region of the early universe has traveled different paths to reach us. While initial analyses from missions like WMAP hinted at some intriguing anomalies, the subsequent highly precise data from the Planck satellite have largely constrained the size of any such cosmic loops. These latest measurements indicate that if the universe does possess a toroidal topology, its characteristic length must be φ, pushing any detectable echoes beyond our current observational reach. This means that, for now, the universe appears to be simply connected, or, if multiply connected, on scales too vast to be directly probed by electromagnetic radiation. Yet this absence of direct evidence does not entirely dismiss the theoretical elegance of a finite, unbounded universe. The question of the universe's global shape remains one of the most profound inquiries in cosmology, touching upon the very nature of existence. If the universe is indeed a closed system, even if incredibly vast, it implies a certain self-sufficiency, a grand cosmic design that does not require an external outside into which it expands. This perspective can evoke a sense of serene completion, where all the matter and energy, all the space-time, exists within a self-contained, endlessly looping configuration. It transforms the concept of an infinite void into a contained, intricate pattern, where every point is, in a profound and fundamental sense, connected to every other. Consider the profound implications for our understanding of cosmic origins. If the universe is a torus, it might offer unique insights into the initial conditions of the Big Bang, perhaps simplifying certain cosmological puzzles by providing a natural boundary condition without needing to invoke an infinite expanse. The very structure of space, if it folds back upon itself, suggests a universe that is both grand in its scale and intimate in its interconnectedness. This geometrical possibility invites us to reflect on the nature of cycles, not just in the lives of stars or the seasons on Earth, but in the very fabric of the cosmos itself. In a toroidal universe, the journey of light, and perhaps even the journey of consciousness, becomes a grand, circular odyssey, always returning, always connected, yet always discovering new perspectives within its self-contained grandeur. This deep, looping characteristic of space offers a tranquil counterpoint to the often overwhelming idea of infinite, unending expansion, cradling our thoughts within a universe that is, in its deepest essence, a harmoniously woven, boundless whole. It is a contemplation that allows the mind to drift peacefully, knowing that even the greatest distances might, in a profound way, lead us back to ourselves. The notion of a finite yet unbounded universe, particularly one with a toroidal topology, challenges our deeply ingrained intuitive understanding of space. Our minds are accustomed to thinking in terms of edges and limits, of a boundary beyond which there is something else, or nothing at all. Yet this cosmic donut, or three torus, demands a different conceptual framework, one where space seamlessly connects with itself, much like the path of an ant on the surface of a globe, forever traversing without encountering an end. The difficulty in truly visualizing such a space stems from our three-dimensional existence. We can readily imagine a two-dimensional surface curving in a higher dimension, but to extend that to our own three-dimensional space, curving within an unseen fourth dimension, requires a leap of abstract thought that stretches the limits of our perception. This mental exercise, however, is not without its rewards. It offers a universe that is both contained and boundless, a paradox that dissolves when one embraces the principles of topology. In a multi-connected space, the very concept of outside loses its meaning, as space itself is the entirety of existence. There is no region beyond the universe. The universe simply folds back upon itself. This can evoke a profound sense of cosmic self-sufficiency, a universe that is complete within its own intricate design. Imagine the feeling of being an explorer, not journeying to the edge of a map, but rather discovering that the map itself has no edge, merely an elegant continuation that brings you back to where you started, enriched by the journey. This cyclical nature, this grand return, offers a tranquil comfort amidst the awe-inspiring scale of the cosmos. One of the most captivating consequences of a multi-connected universe, especially one with a characteristic length roughly comparable to or slightly larger than our observable horizon, would be the possibility of seeing multiple images of the same cosmic objects. This isn't merely a theoretical curiosity, it's a phenomenon that would offer direct, observational proof of the universe's topology. Imagine peering through a cosmic telescope and observing a distant galaxy cluster. In a toroidal universe, the light from that cluster could have traveled along different paths, looping around the universe in various directions, only to arrive at our telescopes as distinct, separate images. Each image would represent the galaxy at a different point in its history, a younger version, an older version, all simultaneously visible to us. Astronomers actively search for these cosmic ghosts or re-entrant images through various observational techniques. One method involves mapping the distribution of galaxy clusters across vast cosmic distances. If our universe is a 3 torus of a certain size, we might expect to find repeating patterns in the arrangement of these clusters, like a giant cosmic fingerprint. Another powerful tool is the aforementioned cosmic microwave background. The faint temperature fluctuations imprinted on the CMB are essentially fossilized sound waves from the early universe. In a multi-connected universe, these fluctuations would exhibit specific correlations or patterns on very large angular scales, reflecting the global shape of spacetime. For instance, certain models predict the appearance of matched circles in the CMB temperature map, where 2 identical patterns of hot and cold spots would appear on opposite sides of the sky, acting as a direct signature of a finite loop geometry. The data from the Planck satellite, our most precise map of the cosmic microwave background, has allowed scientists to place stringent limits on the size of any such cosmic loops. The absence of clear, detectable matching circles or repeating patterns in the CMB, particularly on scales smaller than the observable universe, suggests that if our universe is indeed multi-connected, its characteristic length must be much, much larger than the 46.5 billion light-years of our observable horizon. This means that any light that has looped around and returned to us would have taken far longer than the universe's current age to complete its journey, rendering such ghost images currently invisible. While this is a negative result in terms of direct detection, it is a crucial piece of information. It tells us that our universe, if finite and multi-connected, is so vast in its topological wraparound that it appears effectively infinite and simply connected from our current vantage point. This enduring mystery, this subtle tension between local flatness and potential global curvature, speaks to the profound questions that continue to drive cosmological research. It reminds us that our perception of the cosmos is inherently limited by the speed of light and the finite age of the universe. What lies beyond our observable horizon, both in terms of sheer distance and fundamental topology, remains an arena for theoretical exploration and future observation. The donut universe, while not definitively proven, serves as a powerful thought experiment, urging us to transcend our ordinary spatial intuitions and embrace the possibility of a universe far more intricate and self-contained than we might initially imagine. This grand, silent contemplation of cosmic geometry invites a sense of quiet wonder, a peaceful journey into the depths of abstract thought, as the mysteries of space gently guide you toward rest. The absence of direct repeating patterns in the cosmic microwave background, while seemingly a definitive statement, does not entirely close the door on a universe with a complex global topology. Rather, it refines our understanding, suggesting the distance one would need to travel to loop back to the starting point is significantly that define our observable horizon. This implies a universe that, while perhaps finite in its total volume, is so vast in its self-connection that it appears, from our limited perspective, to be an infinite, boundless expanse. It is a subtle but profound distinction, reminding us that our immediate observational bubble, constrained by the speed of light and the universe's age, is but a small window into the true cosmic architecture. This inherent limitation does not diminish the intellectual pursuit. Instead, it transforms the quest for cosmic shape into a deeper, more nuanced exploration. If the universe's topological folds are beyond our current sight, What does this mean for our philosophical understanding of its grandeur? It suggests that the cosmos might harbor secrets of its geometry that are, for now, beyond direct empirical verification, existing in a realm where theoretical elegance and mathematical consistency guide our contemplation. The idea of a finite, unbounded universe, even if effectively infinite to us, offers a comforting sense of cosmic self-containment, a vast tapestry that, despite its immense scale, is ultimately woven from a finite amount of space and time. We are not lost in an endless void, but rather situated within a grand, intricate design that simply extends beyond our current capacity to perceive its full looping pattern. Beyond the simple three torus, which we have imagined as a donut, other multi-connected topologies exist within the realm of theoretical possibility. One such intriguing model is the Poincare dodecahedral space, where the universe is shaped like a dodecahedron, a 12-sided polygon with opposite faces identified. In this intricate geometry, if one were to exit through a particular face, they would immediately re-enter from the opposite face, creating a complex, finite, and self-contained space. Like the torus, this model could also exhibit zero local curvature, appearing flat on scales smaller than its overall size, thus remaining consistent with current CMB observations. The existence of such a model highlights the rich mathematical landscape of possible cosmic shapes, each offering a unique way for the universe to be finite yet unbounded, a testament to the elegant creativity of space-time itself. These alternative topological models, while more complex to visualize, broaden our understanding of what the universe could be, inviting us to consider forms far removed from our everyday experience. The continuing search for topological signatures, even in the face of current observational constraints, pushes the boundaries of scientific inquiry. Future cosmological experiments with even greater sensitivity and resolution might one day be able to detect the faint, subtle imprints of a multi-connected universe if its characteristic length is only slightly larger than our observable horizon. Gravitational wave astronomy, a nascent but rapidly developing field, could also offer new avenues for probing the universe's global topology. Gravitational waves, ripples in space-time itself, travel unimpeded through the cosmos. If the universe is indeed multi-connected, these waves might also exhibit repeating patterns, or echoes, much like light, providing an independent means to search for cosmic loops. This multi-messenger approach, combining electromagnetic and gravitational wave observations, holds the promise of unlocking deeper secrets about the universe's fundamental architecture. Until such discoveries are made, the ultimate global shape of our universe remains a magnificent mystery. It is a realm of profound uncertainty, where the cosmos whispers possibilities that stretch our imagination to its very limits. This enduring enigma, however, is not a source of anxiety, but rather an invitation to intellectual wonder. It reminds us that our understanding of reality is an ongoing journey, a continuous unfolding of discovery and contemplation. To live in a universe whose true shape is still a subject of active inquiry is to reside at the very edge of knowledge, a privileged position for those who seek to understand the grand design. And in this quiet moment, as you drift towards sleep, consider this profound thought. Whether infinite or a grand, self-connecting loop, the universe is a place of unfathomable wonder. Your own conscious mind, contemplating its vastness and its potential shapes, is an integral part of this cosmic unfolding. You are not separate from this grand design. You are a fleeting, yet deeply connected element within it. The elegance of a finite, unbounded universe offers a sense of ultimate belonging, a cosmic embrace, tranquil sense, linked to every other, a gentle thought to carry you into the quietude of sleep. The current observational limits, particularly those derived from the exquisite detail of the cosmic microwave background, have pushed the characteristic length of any potential toroidal or other multi-connected universe beyond the immediate reach of our direct sight. This means that if the universe does indeed loop back on itself, the scale of this self-connection is so immense, so truly vast, that it far exceeds. For all practical purposes, from our current vantage point within this expanding cosmic tapestry, the universe appears effectively infinite in its spatial extent. Yet this conclusion is not a definitive, unyielding statement on the absolute, true global topology. Rather, it serves as a profound reflection of our current technological and observational capabilities, reminding us that what we perceive is always filtered through the lens of our limited light cone. The universe may still be finite, its total volume a grand, calculable number, simply on a scale so utterly colossal that its ultimate shape remains an elegant theoretical possibility rather than an empirical certainty. It is a silent, cosmic secret held gently within its boundless and profoundly self-referential vastness. This crucial distinction between the observable universe and the actual global universe invites a deeper philosophical inquiry into the nature of reality itself. We reside within a unique light cone, a specific bubble of space-time from which electromagnetic radiation has had sufficient time to reach us since the genesis of the Big Bang. What lies beyond this ever-expanding horizon is not necessarily an empty void, nor is it a distinct, disconnected realm. Instead, these unseen regions could be intrinsically and causally connected to our own, forming a seamlessly integrated, looping whole. Imagine, if you will, the experience of a tiny, intrepid vessel navigating an unimaginably vast, intricately folded ocean. From its limited perspective, the ocean might appear to stretch out endlessly in every direction. Yet the full, global extent and true geometry of this ocean, its profound curvatures and self-connections, remain inferred, a subject of abstract mathematical deduction and quiet philosophical contemplation. Our instruments, for all their increasing sophistication, are akin to those small boats, capable of charting only a relatively tiny portion of the boundless surface. The persistent, almost uncanny flatness observed in the cosmic microwave background radiation is, without doubt, a powerful and compelling indicator. It suggests, with a remarkable degree of precision, that is exquisitely close to the critical density required for a geometrically flat space. This local flatness, however, can coexist harmoniously, even beautifully, with a finite, multi-connected global topology. It's a bit like observing a small, infinitesimally flat patch of a very large, subtly curved surface, where the curvature exists, but on a scale so utterly vast that it simply escapes our immediate, localized detection. So, while our immediate local measurements point convincingly towards flatness, and by extension, the possibility of an infinite expansion, the overarching global picture might well be one of a finite, elegantly self-contained cosmos. The universe, in this profound and tranquil view, is not expanding into an outside of anything, for there is no outside. Rather, its own internal space is gracefully stretching, and if that space is topologically closed, it simply means that more of this same interconnected space is continuously being created, but always within an encompassing, finite, and looping structure. This intricate cosmic topology also profoundly influences how we might begin to conceptualize the very nature of time and the delicate dance of causality on the grandest, most majestic scales. In a hypothetical, truly infinite and simply connected universe, events are typically envisioned to unfold in a strictly linear fashion, with distinct and often unambiguous pasts and futures. However, in a multi-connected universe, particularly one where light can, in theory, traverse the universe multiple times, the traditional notion of cause and effect could become subtly, yet deeply, intricate. While no information could ever violate the cosmic speed limit, the potential for light to eventually complete grand, multi-billion-year journeys and return to its origin could, in principle, lead to fascinating and mind-bending cosmological scenarios. Observers might, over immense stretches of cosmic time, eventually perceive their own past or the ancient history of their galaxy, reflected back at them from immeasurable distances. Such a possibility, while currently far beyond our present observational capacity and requiring a characteristic length smaller than what the latest Planck data currently suggests, vividly highlights the profound and utterly unexpected ways in which the universe's underlying geometry could intricately shape its sweeping, grand narrative. It suggests a cosmos where history is not merely a straightforward linear tale, but a beautifully woven, multi-layered epic, rich with recurring motifs, subtle echoes, and deep, resonant connections. The ongoing, tireless quest to unveil the universe's true and ultimate shape is a profound testament to humanity's innate, insatiable drive to comprehend our singular place within the grand, overarching scheme of existence. It continuously forces us to confront the inherent limits of our perception and the breathtaking vastness of what still remains unknown and unexplored. Whether the universe is, in its deepest essence, truly infinite or a magnificent, self-connecting, looping donut, the very act of contemplating these grand possibilities itself expands our consciousness, gently inviting us to transcend our ordinary, everyday notions of space, dimension, and even reality itself. It is within this profound uncertainty, this elegant, overarching mystery, that a deep and abiding sense of calm wonder can be truly discovered and cherished. To acknowledge the theoretical possibility of a universe that is intrinsically self-referential, a cosmos that gracefully loops back upon itself, is to embrace a form of ultimate, comforting interconnectedness. Your very existence, your deepest thoughts, your quiet, rhythmic breathing in this tranquil moment are all, in a profound and literal sense, an integral, interwoven part of this grand, unfolding, and potentially looping cosmic story. This deep and expansive reflection allows us to settle into a more holistic, more serene understanding of our cosmic home, our place within its majestic fabric. We are not merely fleeting inhabitants of a small, insignificant planet orbiting an average star within an isolated galaxy. Instead, we are active, conscious participants in a continuous, perhaps even cyclical, dance of matter and energy, all governed by fundamental laws that permit such astonishing and beautiful geometries. The universe, in its quiet, breathtaking grandeur, might well be a perfectly balanced, utterly self-contained system, an intricate cosmic donut whose seemingly distant edges are, in reality, seamlessly joined, ensuring a perpetual, harmonious flow without any discernible beginning or end in a purely spatial sense. This profound thought, this serene image of an endlessly connected cosmos, can be profoundly soothing, allowing the restless mind to gently release its rigid grip on conventional boundaries and instead embrace the fluid, interconnected, and ultimately tranquil nature of reality. It is a soft, gentle whisper from the universe itself, an invitation to find deep serenity and inner peace within its boundless, yet beautifully structured and eternally embracing expanse as you slowly drift towards the calm of sleep. The current understanding, shaped by the most sensitive instruments peering into the cosmic past, suggests that if our universe embraces a multi-connected topology, its characteristic length stretches far beyond what our observable horizon permits us to witness directly. This means that any grand cosmic loops, any self-connections in the fabric of space-time, are so immensely vast that they appear to us as an effectively infinite expanse. Yet this observational constraint does not diminish the profound elegance of the toroidal universe concept. Instead, it elevates it to a realm where mathematical consistency and theoretical beauty guide our contemplation, inviting us to consider a cosmos that is, in its deepest essence, both finite in its total volume and utterly boundless in its spatial configuration. It is a universe that holds its ultimate secrets with a quiet grace, a grand design whose intricate pattern unfolds far beyond our immediate perception, yet remains perfectly coherent within its own internal logic. This profound realization gently challenges our ingrained human intuition, which often struggles with the notion of a space that has no edge, no outside, into which it expands. We are accustomed to visualizing boundaries, to conceiving of a container that holds everything. But a toroidal universe, or any multi-connected topology, asks us to transcend these familiar conceptual frameworks. It posits a cosmos where space itself is the entirety of existence, a self-contained entity that gracefully folds back upon itself. There is no external void, no beyond the universe, because the universe is everything, intrinsically interwoven and complete. This can be a deeply comforting thought, transforming the vast, potentially intimidating emptiness into a harmonious, self-sufficient whole. It offers a sense of ultimate belonging, where every point in space is, in a fundamental way, connected to every other, a grand, intricate dance without a conventional perimeter. The mathematical models that describe these topologies are not merely abstract constructs. They are expressions of a potential underlying reality, a language through which the universe might reveal its most fundamental truths. John Wheeler, among other visionary physicists, often spoke of the profound connection between physics and information, suggesting that reality might be more akin to a grand computational process. In a finite, multi-connected universe, the total amount of information contained within that space, though immense, would also be finite. This contrasts with an infinite universe, where the information content would likewise be infinite, posing conceptual challenges for some theoretical frameworks. The elegance of a finite information content, even if astronomically large, offers a sense of completeness and computability. A universe whose story, though epic, can ultimately be fully described and understood within its own self-defined parameters. Such a universe also subtly redefines our relationship with cosmic recurrences. While the observable universe is currently expanding, and the likelihood of observing literal ghost images of our own galaxy is incredibly low due to the immense characteristic length, the theoretical possibility of cosmic cycles on truly colossal timescales remains. In a finite space, even one that is expanding, there are arguments that, given enough time, any configuration of matter and energy might eventually repeat. This is a concept that stretches far beyond human experience, touching upon the Poincare recurrence theorem in statistical mechanics, which suggests that systems confined to a finite phase space will eventually return arbitrarily close to their initial state. While the timescales involved are vastly longer than the age of the universe, the mere contemplation of such a possibility, that the cosmic dance might one day repeat its patterns, can evoke a sense of deep, cyclical calm, an affirmation of the universe's enduring, self-renewing nature. This quiet reflection on the universe's geometry and topology invites a profound sense of wonder about our own existence. We, as conscious beings, are observing and attempting to comprehend a cosmos that, by its very nature, might be designed in a way that defies our most basic spatial intuitions. Yet it is precisely this challenge to our assumptions that expands our understanding and deepens our appreciation for the intricate beauty of physical laws. To consider that the space around us, the space we inhabit, might be a part of an endlessly looping, finite structure is to embrace a cosmic intimacy, a sense of being deeply embedded within a self-contained, harmonious whole. Your thoughts, your breath, the gentle rhythm of your heart are all occurring within this grand, elegant, and potentially toroidal expanse. The journey to uncover the universe's ultimate shape is far from over. It is a continuous, evolving quest, driven by new observations, refined theoretical models, and the boundless curiosity of the human mind. Each new piece of data, each new conceptual breakthrough brings us closer to understanding the true nature of our cosmic home, revealing its hidden symmetries and its profound interconnectedness. And as you allow these thoughts to gently settle, as the vastness of space cradles you in its silent embrace, remember that whether infinite or a grand, looping donut, the universe is a place of endless fascination. It is a world of quiet wonders, where the very fabric of reality holds secrets that continue to inspire awe and invite serene contemplation, guiding you softly towards the tranquil depths of sleep, knowing you are a part of this beautifully structured, eternally unfolding cosmic mystery. We have journeyed through the profound implications unbounded, a cosmic enigma whose true shape remains veiled beyond our current observational reach. This notion that the vast expanse we perceive could be a self-connecting loop so immense it appears infinite offers a unique blend of scientific precision and philosophical depth. It is a testament to the elegant subtleties of space-time itself, a fabric that can be locally flat, as our observations suggest, yet globally curved or multi-connected in ways that defy our everyday intuition. The current data, primarily from the cosmic microwave background, strongly supports a universe that is geometrically flat, meaning it conforms to Euclidean geometry on local scales. However, as we've discussed, this local flatness does not definitively preclude a finite, multi-connected global topology where the universe wraps around itself much like the surface of a sphere or a torus, but in three spatial dimensions. This presents a fascinating paradox. A universe that feels infinite in its scale, yet might ultimately be contained within a grand, self-referential structure, a cosmic puzzle patiently awaiting its full solution in the quiet corridors of time. The concept of an effective infinity becomes particularly salient here, offering a crucial bridge between our limited human perception and the universe's potential true nature. If the characteristic length of a toroidal universe, the immense distance one would need to traverse to return to their starting point, is significantly greater than the diameter of our observable universe, which is approximately 93 billion light-years, then for all practical purposes, our cosmos behaves as if it were truly infinite. We would never, not in the entire lifespan of our civilization, nor indeed in the projected future of the universe itself, be able to complete a full loop or observe repeating patterns. The light from any theoretical ghost image of a distant galaxy would simply take far longer than the current age of the universe to complete its journey and finally reach us, rendering such an effect utterly unobservable with any conceivable technology within our cosmic epoch. This practical infinity, despite the underlying theoretical possibility of a finite volume, offers a peculiar and profound comfort. It allows the restless human mind to find deep repose in the idea of boundless expansion, a limitless canvas for cosmic evolution, while simultaneously appreciating the intrinsic mathematical elegance and serene beauty of a closed, self-contained system. It effectively removes the lingering existential anxiety of an edge or a wall that one might conceptually fall off, replacing it with the tranquil and expansive understanding that space simply continues, gracefully unfolding and perhaps looping back on itself on scales so utterly grand they transcend our immediate, everyday human comprehension. This allows for an enduring sense of infinite possibility within a harmoniously contained and deeply peaceful whole. This intricate interplay between theoretical possibilities and the inherent limitations of our current observational capabilities forms the very frontier of modern cosmological inquiry, continuously guiding scientists in their tireless pursuit of cosmic truth. The universe's fundamental geometry, its intrinsic curvature, is, as we understand it, intimately tied to its total density of matter and energy. Our exquisitely precise measurements of the cosmic microwave background, the ancient light from the universe's infancy, tell us that this density is incredibly close to a critical value. If the density were even slightly higher, the universe would possess a positive curvature resembling a grand cosmic sphere, destined eventually to recollapse in a dramatic Big Crunch. Conversely, if it were even fractionally lower, it would exhibit a negative curvature, like an infinitely sprawling saddle shape, expanding forever without end. The observed flatness, therefore, sits on an almost impossibly delicate knife edge, suggesting a profound and precise balance that hints at the powerful underlying mechanisms of its creation, most notably the theory of cosmic inflation. Inflation, The hypothesized epoch of rapid exponential expansion in the very early universe naturally smooths out space-time and rigorously drives its geometry towards flatness, largely irrespective of its initial curvature. This smoothing mechanism is so remarkably efficient that it could take an initially tiny, topologically complex space, perhaps even a nascent miniature donut, and stretch it to absolutely gargantuan proportions, making its inherent self-connections currently undetectable to us. This implies that the universe could indeed be finite, but on such an unimaginably immense scale that its true topology remains a silent, profound cosmic secret, forever beyond our immediate, direct grasp, fostering a sense of enduring mystery and quiet contemplation. The relentless and meticulous search for these subtle topological imprints continues unabated, pushing the boundaries of astrophysical observation and theoretical ingenuity to new heights. Future instruments designed with even greater angular resolution and unprecedented sensitivity might one day be able to probe the cosmic microwave background for faint, elusive correlations on scales that are currently just beyond our reach. These next-generation telescopes, both ground-based and space-based, promise to offer even sharper, more detailed images of the early universe, potentially revealing the subtle echoes that have eluded us thus far, thus refining our cosmic maps. Moreover, the advent of BPI opens entirely new and profound windows into the universe's deepest, most hidden structures. Gravitational waves, being ripples in the very fabric of space-time itself, are not absorbed or scattered by matter in the same way as light, allowing them to carry pristine information directly from the most cat. The journey to fully map the universe's ultimate shape is a continuous endeavor, one that constantly refines our understanding and pushes the boundaries of our perception. Even with the most advanced instruments, the sheer scale of the cosmos, particularly if its topological features exceed our observable horizon, renders it effectively infinite to our current senses. This effective infinity is not a surrender to the unknown, but rather an acknowledgement of the profound elegance of what presents itself to us as boundless, a quiet testament to its grand, intricate design. The current data, particularly from the cosmic microwave background, consistently points towards a universe that is locally flat, a geometric property that, on its own, would typically imply an infinite expanse. Yet the theoretical beauty of a finite, unbounded universe, like a 3 torus, persists as a compelling possibility, a silent cosmic secret held within its majestic vastness. This subtle distinction between local flatness and potential global curvature invites us to consider how such a reality shapes our cosmic worldview. If our universe is indeed a 3 torus, then the very notions of a center or an edge become obsolete in a conventional sense. Just as the surface of a sphere possesses no singular starting point or ending boundary, so too would a toroidal universe be uniformly distributed with no privileged location from which the Big Bang originated. The Big Bang, for instance, was not an explosion in space, but rather the rapid expansion of space itself, a process that unfolded everywhere simultaneously. In a looping cosmos, this means that every point is, in a profound way, the center, and no point is the edge, fostering a deep sense of universal interconnectedness. This abstract understanding removes the intuitive anxiety of an ultimate boundary, replacing it with the tranquil and expansive realization upon. Also resonates deeply with certain concepts in information theory. In physics, information is often considered a fundamental quantity, and an infinite universe would imply an infinite capacity for information storage. A finite universe, even one of immense scale, would naturally contain a finite amount of information, a concept that is often more tractable and consistent with emerging ideas in quantum gravity, such as the holographic principle. This principle, which we have touched upon in other contexts, suggests that the information content of a region of space can be encoded on its boundary, hinting at a universe whose deepest description might be found in its 2-dimensional surface rather than its 3-dimensional volume. In a toroidal universe, this could mean that the entire cosmic narrative, though vast and complex, is ultimately a self-contained story, a finite set of information beautifully arranged within its looping structure. This perspective offers a sense of profound order and completeness, a universe whose grand design is, in a fundamental way, solvable and comprehensible, even if its sheer scale makes it seem unfathomably large. Our human minds, evolved within a three-dimensional, largely Euclidean environment, naturally struggle to fully visualize these higher-dimensional or topologically complex geometries. We are conditioned to think in terms of linear paths, distinct boundaries, and external spaces. Yet the universe, in its majestic indifference to our intuitive biases, might operate on principles that demand a more abstract, more flexible understanding. This very struggle, this stretching of our mental faculties to grasp concepts like a universe that is finite yet unbounded, is itself a path to deeper appreciation and wonder. It fosters a profound humility in the face of cosmic grandeur, reminding us that our internal models of reality are constantly being refined by the universe itself. This intellectual exercise, this gentle push against the limits of our imagination, can be profoundly meditative, allowing the mind to expand its horizons and embrace possibilities that transcend the familiar. The ongoing quest to discern the universe's ultimate shape is, therefore, more than just a scientific endeavor. It is a profound philosophical journey. It reminds us that knowledge is a continuous process, and that the greatest mysteries often reside not in what is dramatically revealed, but in the subtle, persistent questions that shape our understanding of existence. To live in a universe whose true global topology remains contemplation, whether our universe is truly infinite or a magnificent, looping torus, we find a deep and abiding peace. The cosmos, in its boundless and elegantly structured silence, cradles our thoughts, offering a serene backdrop for rest. It is a gentle reminder that we are part of an intricate, self-contained dance where every element, every thought, is interconnected within a grand, harmonious whole, guiding you softly towards tranquil quest to fully comprehend the universe's global shape extends beyond the realm of present-day observation into the intricate tapestry of quantum gravity and the intriguing possibilities of the multiverse. When we delve into the earliest moments of existence during the universe's primordial infancy, the very fabric of space-time was so incredibly dense and energetically active that the familiar laws of general relativity, which describe gravity on large scales, would have dissolved into a realm governed by quantum effects. Theories of quantum gravity, such as string theory or loop quantum gravity, aim to unify these two fundamental pillars of physics, offering glimpses into how space-time itself might emerge from a deeper quantum reality. Within these theoretical frameworks, the universe's initial topology might not have been arbitrary, but rather a natural outcome of these fundamental quantum processes, perhaps favoring certain finite, multi-connected geometries from its very inception. This suggests that the large-scale structure we observe today, including any subtle topological folds, could be a cosmic echo of these incredibly tiny, quantum-level fluctuations in the nascent universe. It's a profound thought that the ultimate vastness of the cosmos might trace its deepest architectural blueprint back to the ephemeral dance of quantum particles, weaving together the unimaginably small with the endlessly grand. Furthermore, the concept of a multi-connected universe finds intriguing parallels and extensions within the broader framework of multiverse theories. Cosmic inflation, the leading model for the universe's rapid expansion immediately after the Big Bang, inherently suggests that inflation might not be a singular event, but an eternal, ongoing process. In this scenario of eternal inflation, our observable universe is merely one of countless bubble universes that have nucleated and expanded from an ever-inflating meta-space. Each of these bubble universes could, in principle, possess its own unique set of physical laws, fundamental constants, and, significantly, its own distinct global topology. Some might be open and infinite, others closed and spherical, and a vast number could be toroidal, like the donut universe we've explored. This perspective transforms the question of our universe's shape into a statistical one. What topologies are most likely to emerge from the eternal inflationary landscape? It implies that the cosmic design we inhabit, with its observed flatness, might simply be one of the countless variations within an infinitely diverse ensemble of realities. This concept, while speculative, adds another layer of profound wonder to our understanding, suggesting that the very uniqueness of our cosmic home might be contextualized within a much larger, endlessly generating, and topologically varied multiverse. It offers a sense of profound possibility, where every conceivable cosmic shape might find its expression somewhere within this grander, overarching reality. The persistent quest to uncover the universe's ultimate shape, therefore, remains a vibrant and essential endeavor, pushing the boundaries of scientific inquiry and philosophical contemplation. It is a journey that continuously refines our understanding of space, time, and existence itself. Whether future observations or theoretical breakthroughs eventually reveal our universe to be truly infinite, or a magnificent, self-connecting torus on an unimaginably vast scale. The very act of seeking these answers enriches our human experience. It fosters a profound humility, reminding us that our perception is limited, yet our capacity for wonder is boundless. As these grand thoughts gently settle within your mind, allow the immense scale and intricate possibilities of the cosmos to lull you into a state of deep serenity. For in this tranquil exploration of universal mysteries, you are not merely an observer, but an integral part of the universe's ongoing dance, connected to its vastness and its elegant design, drifting softly towards the peaceful embrace. This profound sense of being woven into the very fabric of existence, a tiny yet aware node in a potentially looping cosmic network, dissolves the anxieties of isolation, replacing them with a quiet affirmation of universal belonging. Awaiting further insight. This fascinating interplay between a locally flat appearance and a potentially multi-connected global topology introduces deeper questions about the fundamental laws that govern the cosmos. If our universe were indeed a cosmic donut or a Poincaré dodecahedral space, its unique geometry could, in principle, subtly influence the behavior of light and matter over truly immense distances, even if these effects are currently beyond our detection thresholds. For instance, some theoretical models explore whether fundamental constants, those seemingly immutable numbers that define our physical laws, might vary ever so slightly along these cosmic loops. While current observations strongly suggest that these constants are uniform across the observable universe, the possibility of minute, topologically induced variations on scales larger than what we can presently measure remains an area of active theoretical investigation. This hints at a universe where its grand architecture might not only define space, but also subtly modulate the very rules by which matter and energy interact, weaving geometry and physics into an even more intricate tapestry of existence. One of the historical motivations for exploring finite topologies, such as the Poincaré dodecahedral space, was to address what cosmologists once termed the horizon problem. This problem arose from the observation that the cosmic microwave background is remarkably uniform in temperature across the entire sky, even for regions that, according to standard Big Bang cosmology, should never have been in causal contact. Inflation theory largely resolved this by proposing an exponential expansion that stretched a tiny, causally connected region into the vast observable universe. However, some multi-connected models offered an alternative solution, suggesting that seemingly disconnected regions were, in fact, topologically connected from the very beginning, allowing for thermal equilibrium. While modern inflation models are robust, the elegance of these topological solutions underscores the profound impact that the universe's global shape could have on our understanding of its earliest moments and its fundamental properties. It reminds us that the universe's initial conditions, its primordial blueprint, might have been far more intricate and topologically rich than a simple, infinite expanse. The universe's relentless, accelerating expansion, driven by the mysterious force known as dark energy, further complicates our understanding of its ultimate size and fate, even within a toroidal framework. If the universe is a finite, multi-connected space, how does this expansion manifest? It means that the internal volume of this cosmic donut is continuously stretching, growing larger, not expanding into anything external, but rather creating more of its own intrinsic space. This is a crucial conceptual shift. The universe isn't a balloon inflating within a larger room. It is the entire room itself, whose walls are continuously moving apart. This ongoing expansion, even within a finite topology, ensures that the perception of effective infinity persists, as the characteristic length of the loops would also continuously stretch, making any repeating patterns even harder to detect over time. This dynamic interplay between an expanding fabric and a potentially finite looping structure offers a deeply tranquil image of cosmic perpetual motion, a grand, silent dance of creation and expansion within a self-contained, boundless whole. As we gently drift into these profound considerations, the personal connection to the cosmos deepens. To contemplate a universe that might be a grand, looping donut or a complex dodecahedron is to embrace a reality far richer and more intricate than our immediate perceptions suggest. It is a universe where the most distant reaches are, in a profound and almost mystical sense, connected to our own local space, a continuous, unbroken fabric. This thought can be immensely comforting, dissolving the anxieties of isolation and reminding us that we are not merely fleeting observers, but integral parts of an elegant, self-referential design. Our conscious minds, capable of grappling with such abstract and majestic concepts, are themselves a testament to the universe's capacity for self-awareness, a brief yet profound flicker within its grand, evolving story. The future of cosmological research, therefore, continues to explore these profound possibilities. Advanced gravitational wave observatories like LISA, designed to detect ripples in space-time from distant cosmic events, could offer a new, independent avenue for probing the universe's global topology. Unlike light, gravitational waves are not affected by matter, allowing them to travel freely from the universe's earliest moments, potentially carrying pristine topological signatures that electromagnetic radiation cannot. Such gravitational echoes, if detected, would provide an unprecedented glimpse into the universe's true shape, offering empirical evidence for or against models like the donut universe. Furthermore, ongoing theoretical developments in quantum gravity and string theory continue to explore the fundamental origins of space-time, offering new mathematical insights into why certain topologies might be favored by nature. These tireless efforts, driven by an insatiable curiosity, slowly, meticulously, piece together the grand cosmic puzzle, revealing new facets of its serene and majestic. Allow these grand ideas to gently settle in your mind. Let the immensity and intricate beauty of the universe. Whether our cosmos is truly infinite or a magnificent self-connecting loop, the very act of contemplating its profound questions expands your spirit, reminding you that you are a part of something truly extraordinary. You are a conscious thread in the universe's grand tapestry. Allow this tranquil understanding to cradle you as you drift softly towards the peaceful embrace of sleep, knowing that the cosmos, in all its silent grandeur, holds you gently within its boundless and eternal mystery. May these deep thoughts about the universe's enigmatic size, from its observable boundaries to the profound possibilities of a donut-shaped cosmos, carry you into a world of tranquil sleep. We have traversed the subtle distinctions between local flatness and global topology, explored the whispers of cosmic echoes, and embraced the idea of an effective infinity that paradoxically resides within a potentially finite, self-connecting whole. The universe, in its majestic silence, continuously invites us to stretch the limits of our imagination, to see beyond the immediate and ponder the truly profound. Whether it unfolds as an endless expanse or a grand looping tapestry, its intricate design speaks of a fundamental order and an enduring beauty that transcends our everyday perceptions. You are not merely an observer of this cosmic dance, but an integral part of its ongoing story, a brief yet conscious flicker within its boundless and elegant architecture. Let this understanding of profound interconnectedness settle gently within your mind. The universe, in all its mystery and grandeur, cradles you, a tiny yet aware element within its vast, intricate design. Fall asleep with this feeling of serenity, knowing that your existence is woven into the very fabric of space-time, part of a cosmic narrative that is both endlessly complex and harmoniously complete. Good night. Our journey into the cosmic beyond begins with understanding what we can actually perceive. We often speak of the universe, but what we truly refer to as our immediate cosmic neighborhood is the observable universe. This is not, crucially, the entire cosmos, but rather a spherical region of space that encompasses all matter and energy whose light has had enough time to travel across the vastness and reach us since the Big Bang. Think of it, if you will, as our personal cosmic horizon, a boundary defined not by any physical wall or barrier in space, but by the fundamental and immutable finite speed of light. This speed, a constant of nature approximately 300,000 kilometers per second, is the ultimate cosmic messenger, carrying information and the very essence of distant events across the immense distances of space. But it takes time to travel. The universe, as we currently understand it, through the lens of modern cosmology and meticulous observation, began its grand unfolding approximately 13.8 billion years ago. One might then intuitively, and quite reasonably, assume that the observable universe, the sphere of all we can see, extends for a radius of simply 13.8 billion light-years in every direction. However, this is precisely where the dynamic and ever-evolving nature of space-time introduces a truly fascinating and often counterintuitive twist. The cosmos has not been static. It has been expanding continuously throughout its entire history. This is not merely galaxies moving through a fixed space, but rather a continuous stretching and growth of the very fabric of space itself, carrying galaxies and all celestial objects further apart from one another over cosmic eons. So, the light we are receiving now from a galaxy that emitted its photons 13.8 billion years ago has not merely traveled a static, unchanging distance. Instead, it has journeyed across space that has stretched and grown considerably during that immense span of time. Imagine, if you will, being a tiny observer on a small raft floating on the surface of an enormous, expanding balloon. As you look out, you can only see the light from other tiny points on the balloon that have had enough time to reach your raft. But while that light travels, the balloon itself is steadily inflating, carrying those distant points further and further away. When the light finally arrives at your raft, the object that originally emitted it is now much, much farther from you than the original distance the light traversed. This intricate dance of light travel and cosmic expansion is precisely what happens with our universe. When we observe these ancient photons, we are essentially seeing objects as they were in the distant past, at the moment their light began its journey. Yet the current, present-day position of those self-same objects is, in fact, much, much farther away than the original distance the light traversed. Current cosmological models, which are robustly supported by a wealth of observational data gathered from powerful telescopes and advanced instruments, including the precise measurements of the cosmic microwave background radiation, that faint, uniform glow which is the relic light from the universe's infancy, and the intricate distribution of galaxies across the heavens, allow us to estimate the current radius of the observable universe to be approximately 46.5 billion light-years. This astonishing figure highlights the immense and almost unfathomable scale of the cosmos, even within the practical confines of what is, in principle, detectable by our most sensitive instruments. It is a vast, ever-growing sphere of cosmic awareness, constantly expanding as more light from increasingly distant regions finally reaches us, revealing new, ancient vistas of galaxies and structures that have been traveling away from us for billions of years. This concept of an observable horizon is deeply rooted in the groundbreaking work of pioneering astronomers and physicists who dared to look beyond immediate perception and question the conventional. Edwin Hubble, for instance, in the 1920s, provided the crucial observational evidence for the expanding universe, a revolutionary concept that was later refined and elaborated upon by countless brilliant scientists like Georges Lemaitre and Albert Einstein, whose theories of general relativity provided the theoretical framework. Hubble's meticulous observations showed unequivocally that distant galaxies are receding from us, and most remarkably, the farther away they are, the faster they appear to move. This grand cosmic expansion, which is now understood to be predominantly driven by a mysterious force we refer to as dark energy, is not merely galaxies moving through a static space, but rather space itself, stretching and growing between them, carrying them along in its profound flow. The implications of this are profoundly philosophical and scientifically challenging. What we perceive as the visible universe is fundamentally a snapshot of the past, a mosaic of ancient light, and the true extent of where those celestial objects are now is far, far greater than their light travel time alone would suggest. This boundary, the very edge of our observable universe, serves as a profound and humbling reminder of our unique, transient place within the vast cosmic tapestry. It tells us, with scientific certainty and the elegant precision of physics, that there is an inherent limit to what we can ever directly perceive, a cosmic veil drawn not by any physical barrier in the traditional sense, but by the fundamental laws of physics and the finite yet immense age of the universe. Yet this inherent limit does not, by any means, imply an end to existence itself. It simply marks the extent of our current, measurable knowledge, the farthest, faintest whisper of light that has managed to traverse the immense expanding void to finally reach our telescopes, and through them, our consciousness. This profound realization that our observable sphere is but a fraction of a potentially far grander whole invites a sense of tranquil wonder, a meditative contemplation of the unseen, and a deep appreciation for the subtle yet immensely powerful forces that continue to shape our reality. We, as conscious beings, are an integral part of this grand unfolding, our very existence woven into the intricate, expanding fabric of an ancient cosmos, forever gazing outwards from our unique vantage point, limited yet boundless in our capacity for understanding. This unobservable region, stretching infinitely or finitely beyond our cosmic horizon, is certainly not empty. Based on the cosmological principle which posits that the universe is homogeneous and isotropic on large scales, meaning it looks roughly the same in all directions and at all locations when averaged over vast distances. We infer that this unseeable expanse contains matter and energy, galaxies and clusters, just like our observable portion. The fundamental laws of physics, as far as we understand them, are almost certainly consistent across this larger, unobservable universe. It is merely a region from which light has not yet had sufficient time to travel the immense, ever-growing distances to reach us. Or perhaps, due to the accelerating expansion, it never will. This implies a universe far grander, far more extensive, and potentially far more complex than our current perceptions allow. A universe whose true, ultimate scale remains one of the most compelling and beautiful mysteries in modern cosmology, beckoning us to ponder what lies just beyond the reach of our sight, yet still within the boundless grasp of our imagination. The observable universe, then, is not the entire universe, but merely our universe, the portion of the cosmos that has revealed itself to us over the span of cosmic time, a fleeting glimpse into an immeasurable whole. Having pondered the boundaries of our observable universe, that luminous sphere whose light has reached us across 13.8 billion years of cosmic expansion, we naturally arrive at an even more profound question. What lies beyond that horizon? What is the true size of the entire universe? This inquiry leads us away from direct observation and into the realm of theoretical physics and the very geometry of space-time itself. The answer, scientists believe, is intricately linked to the overall shape of the cosmos. Cosmologists speak of three fundamental possibilities for the universe's geometry. It could be flat, open, or closed. Imagine for a moment a two-dimensional analogy to help visualize these complex concepts. A flat universe is much like an infinite, flat sheet of paper, stretching endlessly in every direction. If you were to draw two parallel lines on this surface, they would remain parallel forever, never converging, never diverging. An open universe, on the other hand, resembles the surface of a saddle curving outwards in every direction. On such a surface, two parallel lines would gradually diverge from each other. Finally, a closed universe is akin to the surface of a sphere, like our own Earth. A sphere's surface, they would eventually converge and cross, much like lines of longitude meeting at the poles. The crucial distinction here is that while a sphere is finite in area, it has no edges or boundaries. You could travel endlessly upon its surface without ever encountering a wall or an end. The geometry of our three-dimensional universe determines its ultimate fate and its overall size. If the universe is truly flat or open, then it is, in all probability, infinite in extent. It would simply stretch on forever, without end, without boundary. If, however, it is closed, then it would be finite, much like the surface of a sphere, yet still without any edges. You could, in principle, travel in a straight line for an unimaginably vast distance and eventually return to your starting point, having traversed the entire cosmic expanse. This finite but unbounded nature is a concept that challenges our everyday intuition, which tends to associate finitude with a boundary. How, then, do we discern the true shape of something so immeasurably vast? Scientists employ sophisticated methods, primarily by studying the faint afterglow of the Big Bang itself, the cosmic microwave background, or CMB. This ancient light, released when the universe was only about 380,000 years old, carries the imprint of the universe's early geometry. Imagine the CMB as a kind of cosmic baby picture filled with tiny temperature fluctuations. These fluctuations represent the seeds of all the galaxies and structures we see today. The angular size of these hot and cold spots in the CMB provides a critical clue to the universe's curvature. If the universe were closed, these spots would appear larger than they truly are. If it were open, they would appear smaller. But if the universe is flat, they would appear precisely as they are, without any distortion. And what have our most precise measurements, gathered by missions like the Wilkinson Microwave Anisotropy Probe, or WMAP, and the Planck satellite, revealed? They have shown, with remarkable accuracy, that the universe is extraordinarily flat. These observations are so compelling that modern cosmological models are built upon this assumption, suggesting that the universe's geometry is very close to Euclidean, or flat. This flatness means that, on the largest scales, space behaves as we would expect from classical geometry, without any significant overall curvature. This finding has profound implications for the question of the universe's total size. A perfectly flat universe, by its very nature, would be infinite. It would stretch without end, a boundless expanse of galaxies, stars, and cosmic structures. However, even if the universe is not perfectly flat, but merely very nearly flat, as our current data strongly suggest, it could still be so incredibly vast that it is practically indistinguishable from infinite on any scale we could ever hope to observe or measure. Think again of our analogy of the Earth's surface. To a tiny ant walking on a vast field, the surface appears perfectly flat, even though it is part of a much larger curved sphere. The curvature is simply too subtle to be perceived on the ant's local scale. Similarly, the universe could possess a subtle curvature, but on a scale so immense that our observable horizon is but a tiny, seemingly flat patch within it. This apparent flatness is also one of the compelling successes of the theory of cosmic inflation. This revolutionary idea proposes that in the merest fraction of a second after the Big Bang, the universe underwent an incredibly rapid exponential expansion, stretching space by factors almost beyond comprehension. This violent yet elegant stretching would have smoothed out any initial curvature the universe might have possessed, much like inflating a wrinkled balloon to an enormous size makes its surface appear smooth and flat. If inflation occurred, it would have pushed vast regions of the universe far beyond our current observable horizon, making the total cosmos astronomically larger than the portion we can currently perceive. The observable universe, therefore, would be merely a small local bubble within a much, much grander and potentially infinite cosmic tapestry. This understanding shifts our perspective from merely observing the universe to recognizing that our very perception of its size is constrained by the speed of light and the history of its expansion. We are, in essence, within a cosmic bubble, and while we can never directly see beyond its edge, the overwhelming evidence from physics and cosmology suggests that the universe continues, vast and perhaps endless, in every direction. This realization that we are part of something so immeasurably grand, something that extends far beyond the reach of our most powerful telescopes, can evoke a deep sense of calm and wonder. It invites us to contemplate our place within this boundless expanse, knowing that the laws of nature that govern our small corner of existence are likely at play across an unimaginably larger, yet unseen, cosmos. Our contemplation of the universe's geometry, particularly its observed flatness, leads us to a truly mind-bending possibility. If the universe is indeed spatially infinite, then what are the profound implications of such boundless expanse? In an infinite universe, every conceivable arrangement of matter, every possible cosmic configuration, must eventually repeat itself. This is not a mere poetic notion, but a logical consequence of infinite space, coupled with a finite number of quantum states that matter can occupy within any given volume. Imagine, if you will, a vast, endlessly stretching cosmic tapestry. Somewhere within that infinite canvas, far beyond our observable horizon, there might exist another galaxy identical to our Milky Way, another star system precisely like our own solar system, and perhaps even another Earth, where life has unfolded in an eerily similar fashion. And if space is truly infinite, then not just one, but an infinite number of such repetitions could exist, each one a cosmic echo of our own reality. This concept, sometimes referred to as a Type 1 multiverse, arises naturally from the idea of an infinite, flat universe. It suggests that the entirety of existence is far grander than our single, observable bubble. The implications for our perception of uniqueness are both humbling and awe-inspiring. If every atom, every thought, every memory is merely a pattern, and that pattern can repeat in an infinite space, then our individual existence, while profoundly real to us, might also be part of an endlessly recurring cosmic narrative. This isn't to diminish the preciousness of our unique lives, but rather to expand the canvas upon which that uniqueness plays out, suggesting an ultimate interconnectedness within an unimaginably vast, perhaps infinite, cosmic whole. Yet the idea of an infinite universe, while logically consistent with current data, is not the only theoretical path to a cosmos far larger than our observable realm. We must also consider the remarkable theory of cosmic inflation, which we touched upon briefly in our earlier discussion. Inflation posits that in the earliest moments after the Big Bang, space-time underwent a period of incredibly rapid, exponential expansion. This burst of growth was so immense that it stretched the nascent universe to an extraordinary scale, far beyond what we can currently see. But what if this inflationary process, this cosmic stretching, did not simply stop everywhere at once? Modern theoretical models of inflation, particularly those involving eternal inflation, suggest that this rapid expansion might continue indefinitely in some regions of space-time, while ending in others. Think of it like a frothing ocean where new bubbles are constantly forming and detaching from the main body of water. Each of these bubbles, according to this theory, could represent a separate universe, a distinct cosmic domain with its own set of physical laws and fundamental constants. Our own universe, then, would simply be one such bubble, one localized region where inflation ceased, allowing matter and energy to coalesce and form the stars and galaxies we observe. This is the essence of the Type II multiverse, often called the bubble multiverse or inflationary multiverse. These other bubble universes would not be next door in any conventional sense. They would be entirely separate space-time domains, effectively unreachable and unobservable from our own. The space between these bubbles would still be undergoing rapid, eternal inflation, effectively isolating each universe from its neighbors. Therefore, even if we were to travel at the speed of light for billions of years, we would never reach another bubble universe, because the intervening space would be expanding away from us far faster than we could ever hope to traverse it. This profound isolation means that while these other universes are hypothesized to exist, we can never gather direct observational evidence of them. Their existence remains an elegant and compelling inference from the underlying physics of inflation. The very idea of a multiverse, whether of the infinite repetition type or the bubble universe variety, reshapes our understanding of cosmic uniqueness. It suggests that the conditions that allowed for the emergence of life, the precise tuning of fundamental constants that govern the interactions of particles and forces, might not be a singular cosmic accident, but rather one outcome among an immense, perhaps infinite, ensemble of possibilities. In some other bubble universe, gravity might be far stronger, crushing matter before stars could form. In another, it might be so weak that galaxies could never coalesce. This perspective offers a tranquil yet profound explanation for the seeming fine-tuning of our own universe, suggesting that we simply inhabit one of the universes where the conditions were just right for our existence to unfold. Such theories, while speculative, are deeply rooted in the mathematical frameworks of general relativity and quantum mechanics, extending our understanding of space and time to scales that defy direct experience. They represent humanity's continuing quest to comprehend the ultimate nature of reality, pushing the boundaries of what is knowable and what can only be inferred through the elegance of theoretical physics. The concept of an entire cosmos stretching far beyond the limits of our vision, populated by an unimaginably vast number of galaxies and potentially even other universes, does not diminish our own existence. Instead, it elevates it, placing our brief moment of consciousness within an almost infinite tapestry of cosmic possibility. To ponder such scales is to engage in a profound form of meditation, allowing the mind to wander beyond the familiar, to embrace the vast unknown with a sense of calm wonder, finding serenity in the boundless mysteries that still beckon from beyond the observable horizon. The profound questions about the universe's ultimate size and the existence of a multiverse naturally lead us to consider the very forces that shape its destiny, particularly the enigmatic influence of dark energy. This mysterious component, which constitutes approximately 68% of the universe's total energy density, is responsible for the accelerating expansion of space. It is not merely a passive phenomenon, but an active, repulsive force that drives galaxies further apart, causing the cosmic fabric to stretch at an ever-increasing rate. This acceleration has a direct and crucial impact on our ability to perceive the universe beyond our observable horizon. As space expands at an accelerating pace, light from increasingly distant regions becomes redshifted to such an extreme degree that it effectively falls off our cosmic event horizon. Imagine a light source in a rapidly expanding space. Even if the light is emitted, The space between the source and the observer stretches so quickly that the light waves are elongated, their energy diminished, and eventually they may never reach us. This means that parts of the universe that were once observable or would have become observable in the distant future are now or will eventually become permanently beyond our causal reach. The cosmic horizon, therefore, is not static. It is a dynamic boundary that is constantly being outpaced by the accelerating expansion. This implies that even if the universe is infinite, the portion of it that we can ever hope to interact with or even know about is effectively shrinking in terms of its causal connection to us over vast cosmic timescales. It is a sobering thought, yet one that speaks to the profound, almost overwhelming power of the universe's inherent dynamics. This relentless expansion, fueled by dark energy, ensures that the observable universe, despite its immense scale of 46.5 billion light-years in radius, will only ever be a fraction of the entire cosmos. What lies beyond this ever-receding horizon is not simply more of the same, but a realm that is slipping away from our direct perception at an accelerating speed. The entities within it, the galaxies and structures, are not merely moving away from us, but the very space between us and them is stretching. This stretching means that light signals sent from those regions, even if they were emitted at the very beginning of time, may never reach us, as the distance they must traverse grows faster than the light itself can travel. This cosmic race is a fundamental aspect of the universe's large-scale evolution, reminding us that our view is always a partial one, a limited window into an endlessly unfolding reality. Furthermore, our current understanding of cosmology suggests that the universe is not just a uniform expanse of gas and galaxies, but is organized into a vast, intricate structure known as the cosmic web. This immense network consists of colossal filaments of galaxies and dark matter, separated by enormous, almost empty voids. Observations from projects like the Sloan Digital Sky Survey have mapped these structures across billions of light-years, revealing a breathtaking cosmic architecture. These structures, like colossal threads woven through the fabric of space, extend far beyond our observable horizon. The continuous nature of this cosmic web, its apparent homogeneity and isotropy on the largest scales, strongly implies that the universe beyond our sight is not fundamentally different from the part we can observe. It is simply more of the same grand, structured expanse, stretching into realms yet unknown to us. The existence of the cosmic web, shaped by gravity and dark energy over billions of years, reinforces the idea of a continuous universe that extends far beyond our current observational limits. We are merely embedded within a small section of this vast, interconnected network. The patterns and formations we observe, the clusters, superclusters, and voids, are not unique to our observable sphere, but are expected to be replicated and extended into the unseeable depths. This gives us a sense of a larger, coherent reality, one that operates under consistent physical laws, even if we cannot directly witness every part of it. It offers a profound sense of scale, suggesting that our observable universe, with its hundreds of billions of galaxies, is merely a single node in an infinitely larger, endlessly repeating, or eternally varied cosmic design. As we delve into these theoretical constructs, it is important to remember that our understanding of the universe, while remarkably advanced, is still incomplete. There may be entirely new physics, new fundamental forces, or even higher dimensions that we have yet to discover, which could further redefine our perception of the universe's true size and nature. Concepts from quantum gravity, such as loop quantum gravity or string theory, attempt to unify all fundamental forces and describe the very fabric of spacetime at its most elemental level. These theories, though highly speculative, hint at structures and scales that could profoundly alter our understanding of the cosmos, perhaps revealing an even grander, more intricate reality than we currently imagine. The pursuit of these deeper truths represents humanity's ongoing intellectual journey, a calm and persistent effort to unravel the universe's ultimate secrets, one scientific discovery at a time. In contemplating these vast scales and the limits of our perception, we are invited to a profound moment of reflection. Our human existence, fleeting and localized as it may seem against the backdrop of an expanding, potentially infinite universe, is nonetheless a remarkable expression of cosmic complexity. We are the universe, in a sense, becoming aware of its own grandeur, its own mysteries. To acknowledge the vastness beyond our immediate grasp is not to feel insignificant, but rather to feel a part of something immeasurably larger and more enduring. It is a tranquil thought that the very atoms within us are a product of this cosmic unfolding, and our consciousness, however brief, offers a unique lens through which to marvel at its infinite possibilities. Our journey through the observable universe and into the theoretical realms of its potential. Infinite geometries brings us face to face with an even more striking consequence of cosmic expansion, the concept of the future visible universe. While our current observable horizon is a sphere in radius, shaped by the speed of light and the age of the universe, the relentless acceleration driven by dark energy implies a future where our cosmic view will paradoxically shrink. Galaxies that are currently within our observable reach, or those whose light we anticipate receiving in the distant future, will eventually be carried away by the stretching of space itself at speeds exceeding the speed of light, effectively receding beyond a point of no return. This phenomenon, often described as a cosmic event horizon, is not a physical barrier, but a fundamental limit to what we can ever causally connect with. It means that there is a boundary beyond which light emitted today will never reach us, no matter how long we wait, because the space between us and the source will expand faster than light can travel. Therefore, the future observable universe, the collection of all regions from which we could ever receive a signal, is actually finite. It is a smaller volume than the current observable universe, because many galaxies we see today will eventually cross this future horizon, and their light will fade into an unobservable void. This is a profound, almost melancholic aspect of our cosmic reality, implying that even if the universe is infinite, our ultimate, measurable grasp of it is not. This leads us to one of the most significant and perplexing puzzles in modern physics: the cosmological constant problem. Dark energy, the driving force behind this accelerating expansion, behaves much like the cosmological constant that Albert Einstein initially introduced into his equations of general relativity, then later famously called his biggest blunder. Yet observations have confirmed that such a repulsive force exists. The puzzle arises when theoretical physicists attempt to calculate the expected value of this vacuum energy, the energy inherent in empty space, based on quantum field theory. These calculations yield a value that is an astonishing 120 orders of magnitude larger than what astronomers actually observe for dark energy. This gargantuan discrepancy between theoretical prediction and observational reality is arguably the greatest unsolved problem in fundamental physics. Why is this vacuum energy so incredibly small, yet non-zero? If it were much larger, the universe would have expanded so rapidly in its infancy that matter could never have coalesced to form stars, galaxies, or indeed, life. If it were exactly zero, the expansion might decelerate, or even reverse, leading to a big crunch. The observed value of dark energy, tiny but significant, seems almost fine-tuned for the existence of a stable, complex universe like ours. This precise tuning is one of the strongest arguments for the existence of a multiverse, particularly the Type 2, or bubble multiverse concept we discussed earlier. In this scenario, our universe is but one bubble among an infinite ensemble, each with slightly different physical constants, including the value of dark energy. We simply find ourselves in the universe where these constants allowed for our existence. This anthropic principle offers a possible, albeit still speculative, resolution to the cosmological constant problem, suggesting that the real size of existence is not merely the spatial extent of our universe, but the vast, diverse collection of all possible universes. Our universe, with its peculiar life-permitting value of dark energy, is then not an improbable cosmic accident, but a statistically inevitable outcome within a much grander, multifaceted reality. This perspective shifts the focus from a single, unique cosmos to an almost infinite landscape of physical laws and phenomena, each playing out its own unique cosmic story. The cosmological constant problem and the accelerating expansion of the universe serve as powerful reminders of the limits of our current scientific models and the profound mysteries that still lie at the heart of reality. They challenge us to look beyond the immediate and the observable, to consider the possibility that the universe is far more intricate and expansive than our current instruments can detect, or our current theories can fully explain. The pursuit of a unified theory of everything, one that can reconcile quantum mechanics with general relativity and explain the origin and nature of dark energy, is the ultimate goal of modern physics. It is a quest that continues to push the boundaries of human knowledge, inviting us to contemplate the universe not as a fixed, fully understood entity, but as a dynamic, evolving mystery whose true scale and nature are still being slowly, meticulously unveiled. And so, as we reflect on these concepts, we find ourselves contemplating not just the spatial dimensions of the universe, but the very depths of scientific inquiry. The real size of the universe transcends mere measurement. It encompasses the boundless potential of unseen realms, the profound implications of fundamental forces, and the enduring questions that ignite our intellectual curiosity. It is a tranquil thought that the universe, in all its immeasurable grandeur, continues to unfold its secrets, inviting us to be a part of its ongoing story, a story that extends far beyond our current horizon, into realms of infinite possibility and serene wonder. The universe beyond our observable horizon, whether it represents an infinite expanse of familiar physics or a tapestry of distinct bubble universes, presents a profound challenge to our intuitive grasp of scale and existence. Our minds, evolved within a finite three-dimensional world, naturally seek boundaries, edges, and definable limits to make sense of phenomena. Yet the cosmos seems to defy such neat categorization, inviting us instead to contemplate boundless possibilities that stretch far beyond the confines of our immediate perception. This is precisely where the scientific journey transcends mere empirical measurement and delves into the deeper, more philosophical implications of what it truly means to exist within such an immense, largely unseeable reality. Consider for a moment the very act of observation. Every single piece of information we gather about the cosmos, from the most distant galaxy to the faint afterglow of the Big Bang, reaches us through light or other forms of electromagnetic radiation, or perhaps through the subtle ripples of gravitational waves. Each such signal carries with it a story from a particular point in space-time, a luminous snapshot of the past. As we peer further and further out into the cosmic expanse, we are simultaneously looking further and further back in time, seeing galaxies not as they are now, but as they were billions of years ago when their ancient light first began its journey towards us. But the light from regions beyond our observable horizon, by its very definition, has not yet had sufficient time to reach us. And in some profound instances, due to the accelerating expansion of space itself, it may never reach us at all. This means that a significant, possibly infinite portion of the universe will always remain forever shrouded in cosmic mystery, perpetually beyond our direct sensory and causal reach. This unobservable realm is not crucially empty. It is simply causally disconnected from us, a silent, unseen continuation of the same majestic cosmic drama, playing out its own grand narrative in the profound darkness beyond our view. This fundamental limitation, imposed by the immutable finite speed of light and the dynamic, ever-expanding nature of the universe, forces us to rely heavily on theoretical inference and the elegant language of mathematical models to construct our understanding of the true scale of existence. We infer the remarkable flatness of the universe, for instance, from the intricate patterns observed in the cosmic microwave background radiation, that ancient uniform glow that is a direct echo of the universe's infancy. We hypothesize the mechanisms of eternal inflation and the potential existence of a multiverse from the perplexing fine-tuning of fundamental constants, such as the enigmatic dark energy that drives cosmic acceleration. These are not direct observations in the way we might perceive a nearby star. Rather, they are sophisticated deductions, intellectual leaps grounded in the predictive power of our most robust physical theories. It is a testament to the extraordinary capacity of human reason that even when faced with an unseeable reality, we can still construct coherent, consistent, and deeply beautiful pictures of its potential grandeur and complexity, pushing the very boundaries of what is knowable. The sheer scale, the potential infinitude, or the vast multiplicity of universes can indeed evoke a peculiar sense of cosmic humility, perhaps even a quiet reflection on our singular, fragile existence within such immense possibilities. Yet, rather than diminishing our significance in the grand scheme of things, this profound perspective can, paradoxically, elevate it. For it is precisely within this tiny, observable cosmic bubble on this small blue planet orbiting an ordinary yellow star that consciousness has miraculously emerged, a unique and precious capacity to even ask these questions, to formulate intricate theories, to meticulously gather data, and to gaze out into the boundless dark and ponder the unseeable. Our minds become, in a profound and deeply contemplative sense, the universe reflecting upon itself, a brief but brilliant flicker of awareness in an otherwise silent, sprawling cosmos. We, as sentient beings, are the very instruments through which the universe attempts to comprehend its own bewildering magnitude and intricate design. This powerful realization that our existence, however small in its physical scale, holds the utterly unique and perhaps rare capacity for understanding and self-reflection, offers a tranquil and deeply affirming counterpoint to the overwhelming vastness. The complex interplay of fundamental forces, the intricate dance of particles and fields, the slow, majestic unfolding of cosmic structures, all these processes, stretching across unimaginable distances and eons of time, have converged in our corner of reality to create conditions where life and ultimately conscious thought can arise and flourish. Our present moment, our very breath, every thought we conceive is inextricably woven into this grand cosmic narrative, a brief yet vital chapter in a story that may indeed be without a definitive beginning or an ultimate end. The quest to grasp the real size of the universe is thus not merely a scientific endeavor driven by empirical curiosity. It is, at its heart, an existential one. It encourages a deep meditative appreciation for the delicate and precise balance of physical laws that allow for our reality to be what it is, and for our own being within it. The universe beyond our horizon is not a void of nothingness or an empty expanse. Rather, it is a realm of inferred potential, a testament to the inexhaustible creativity and astonishing complexity inherent in fundamental physical laws. And in contemplating these unseeable depths, these silent, unreachable domains, we come to understand that the true measure of the universe may lie not just in its physical dimensions or the number of galaxies it contains, but in the enduring capacity of consciousness, like our own, to marvel at its own improbable existence within it. We are not separate from this grand cosmic drama. We are an intrinsic, albeit tiny and transient, part of its unfolding wonder, connected to its deepest mysteries. This thought alone, of being intimately connected to such boundless immensity, can bring a profound sense of peace and a quiet, expansive understanding, gently guiding us towards a state of deep tranquility. As we quietly ponder the profound implications of an ever-expanding universe where vast cosmic vistas are perpetually receding beyond our causal reach, we encounter a deeper, more subtle mystery, the very nature of information itself when confronted with these ultimate horizons. In the realm of fundamental physics, and particularly in quantum mechanics, information is considered a bedrock principle, a quantity that is never truly lost, only scrambled or transformed. This steadfast rule forms a cornerstone of our understanding of reality, suggesting a universe where every event, every interaction, leaves an indelible trace. Yet, if galaxies are accelerating away from us at speeds that will eventually prevent their light from ever reaching us, does the information contained within those distant, unreachable realms become effectively lost to our universe? This question touches upon some of the most profound paradoxes in modern science, echoing, in a sense, the black hole information paradox, where matter seems to vanish beyond an event horizon, taking its intrinsic information with it into an unknowable singularity. For the cosmic horizon, however, the principle is perhaps more gentle, more a matter of inaccessibility than outright destruction. It is not that information is annihilated, rather it becomes causally disconnected from us. The light, the electromagnetic waves, the subtle gravitational whispers from these regions simply can no longer traverse the ever-stretching expanse of space to reach our detectors. They are still there in their own cosmic timelines, unfolding their own realities, governed by the same elegant physical laws that apply here. But from our perspective, they have faded into an eternal, unseeable silence, their stories forever unread by us. This concept invites us to consider the universe as a vast, intricate tapestry, where threads of information are constantly weaving and unweaving, but some are simply drawn too far apart for us to ever perceive their intricate patterns directly. Imagine a message sent across a rapidly widening chasm. The words are spoken, the information exists, but the gap grows faster than the sound can travel. Cosmos will always remain forever shrouded in. It is a tranquil thought that even in its inaccessibility, this distant cosmos continues its dance, unfolding in a serenity that transcends our immediate perception. This inherent unknowability, this cosmic veil drawn by the very laws of nature, cannot directly observe, yet we can reason and deduce. Scientists continue to probe these questions not through direct observation, but through the elegant frameworks of mathematics and theoretical physics. They build models, test hypotheses against the observable data, and derive inferences about the grander whole, much like an archaeologist reconstructs an entire ancient city from scattered fragments. For instance, the astounding consistency of the cosmic microwave background radiation across the entire observable sky, a puzzle known as the horizon problem, suggests that regions of the universe that are now causally disconnected must have once been in close contact, allowing for thermal equilibrium before being stretched far apart. This is a powerful piece of evidence supporting the theory of cosmic inflation, which posits that the early universe expanded so rapidly, exponentially, by factors almost beyond comprehension, that these distant regions were once much closer, allowing for their uniform temperature before being stretched far apart into the vast expanse we see today. Inflation, therefore, implies a universe far, far larger than our observable bubble, so immense that our horizon is but a tiny uniform patch within it. The continuous nature of these theoretical frameworks, consistently predicting a universe vastly larger than what our instruments can detect, invites a sense of serene acceptance. It suggests that our quest to understand the cosmos is not about finding an ultimate edge or a definitive size in the conventional sense, but about embracing the inherent infinitude or the immeasurable scale of reality. This journey of understanding transforms the unknown from a source of apprehension into a source of tranquil wonder. We are not meant to grasp every detail of the infinite, but rather to appreciate the profound elegance of the laws that govern it, even in its unseeable depths. Our minds, with their finite capacities, are stretched and expanded by these concepts, much like the universe itself, growing in complexity and awareness, finding a quiet harmony in the face of such profound mystery. The very act of contemplating these boundless scales, of imagining universes beyond our own or an infinite expanse of our own, changes our perspective on our own existence. It reminds us that we are woven into a tapestry of reality that extends far beyond our immediate experience, a tapestry whose threads are cosmic in scope. This connection to the vastness, to the deep, silent processes that unfold across cosmic eons, can be profoundly calming. It allows us to view our lives not as isolated events, but as integral parts of a grand, ongoing cosmic story. A story that began long before us and will continue long after, in realms both seen and unseen. It is a narrative of matter and energy, of space and time, of forces and fields, all dancing in an eternal ballet, creating and recreating forms of astonishing beauty and complexity. Our brief moment of consciousness, our capacity for thought, our ability to ponder these very mysteries, is a fleeting yet precious manifestation of this cosmic dance, a unique and irreplaceable note in the symphony of existence, a rare and delicate flower blooming in the vast, dark gardens of space-time. Consider the profound implications if the universe is indeed spatially infinite. In such a scenario, not only would there be an endless continuation of galaxies and structures like our own, stretching out into an endless vista, but the very patterns of matter and energy within this infinite expanse would, by the laws of probability and the finite number of ways particles can arrange themselves, be destined to repeat. Every conceivable arrangement of particles, every configuration of atoms, every sequence of events would inevitably occur an infinite number of times. This means that somewhere, far beyond our current horizon, there exists another Earth, another version of you, living out this very moment, perhaps with a slightly different choice made or an entirely different life path taken. And not just one such copy, but an infinite number of them, each a cosmic twin or a distant echo. This Boltzmann brain type of argument, while unsettling to some, can also be viewed as a serene affirmation of possibility. If everything that can happen does happen within an infinite canvas, then our existence, however improbable it may seem in isolation, is not just a fortunate accident, but an inevitable, beautiful consequence of the universe's boundless nature. It lends a sense of quiet grandeur to the mundane, knowing that the very fabric of reality is so rich with potential that all permutations are, in some distant corner of infinity, brought into being, a silent testament to the universe's inexhaustible creativity. Ultimately, the true size of the universe beyond the observable horizon questions in all of science. It is a question that may never be answered through direct observation, but rather through the relentless pursuit of theoretical elegance and the profound insights offered by mathematics, which serve as our guides into these otherwise unreachable domains. The universe, in its ultimate extent, is likely far grander than our most expansive imaginations can fully encompass. A silent, sprawling canvas upon which the laws of physics paint an endless array of cosmic wonders, from the smallest quantum fluctuation to the largest galactic supercluster. To lie here, contemplating this immeasurable vastness, is to connect with a truth that transcends our human scale, a truth that is both deeply humbling and infinitely inspiring. It reminds us that we are part of a cosmos that is always more, always grander, always more mysterious than we can ever fully grasp. And in that quiet acceptance, that peaceful surrender to the magnificent unknown, we find a profound sense of calm, a gentle invitation to let our minds drift into the expansive, serene depths of sleep, knowing that the universe, in all its true, unfathomable size, continues its majestic, silent unfolding around us, forever and ever. Our minds, in their quest to understand the universe's true scale, often encounter the limits of what can be directly observed, pushing us into realms of theoretical inference and profound philosophical contemplation. We have considered the observable universe, the cosmic horizon, and the implications of an accelerating expansion driven by dark energy, hinting at a cosmos far grander than our current perceptions allow. But what does it truly mean for a reality to be so vast, so encompassing, that it potentially contains endless repetitions or even entirely different universes? This question, while deeply abstract, touches upon the very fabric of our understanding of existence and our place within it. The concept of an infinite universe, where space simply stretches on forever without boundary or end, carries with it a fascinating, almost inevitable consequence: the cosmic recurrence. If space is truly infinite, and the amount of information or matter that can exist within any given finite volume is itself finite, then statistical mechanics dictates that every possible arrangement of particles, every conceivable event, every unique configuration of matter and energy must eventually repeat itself an infinite number of times across this boundless expanse. This means that far beyond our observable horizon, perhaps light years upon light years away, there could solar system precisely mirroring our own, and even another Earth, where a version of you is, at this very moment, listening to these same words, experiencing the same thoughts. This is not a mystical notion, but a logical extrapolation from the combination of an infinite space and the finite nature of quantum states. It suggests that individuality, while precious and profoundly real within our experience, might also be a recurring pattern within an endlessly repeating cosmic design. Such a thought, rather than being unsettling, can foster a deep sense of calm interconnectedness. It implies that the universe is so rich with possibility, so vast in its fundamental capacity, that all potential narratives are, in some distant cosmic corner, brought into being. We are not merely a singular, improbable occurrence, but a resonant chord played endlessly across an infinite symphony. This perspective, while challenging to visualize, offers a tranquil reassurance that our existence, our experiences, our very being, are not isolated anomalies, but part of a grander, more encompassing cosmic dance. Beyond the idea of infinite repetition within a single, vast universe, lies the more radical concept of the multiverse itself, particularly the bubble multiverse arising from eternal inflation. Here, our universe is not merely an infinite expanse, but one of countless distinct bubble universes, each potentially governed by its own unique set of physical laws and fundamental constants. Imagine a cosmic foam, where each bubble is a self-contained reality, an entirely separate space-time. In some of these bubbles, the force of gravity might be others. The electromagnetic force might be different, making stable atoms impossible. Our universe, with its exquisite fine-tuning of constants that allow for the emergence of chemistry, stars, planets, and ultimately conscious life, is then not a miraculous fluke, but simply one of the many us to exist. This interpretation, known as the anthropic principle, is often invoked to address the profound puzzle of the cosmological constant. If there are an infinite number of universes, each with a different value for this mysterious dark energy, then it becomes statistically probable that at least some of them would possess a value precisely tuned to allow for the vast, slow cosmic evolution necessary for life to arise. We, as observers, naturally find ourselves in one of those rare, life-permitting universes. This perspective transforms the seemingly improbable into the inevitable within a grander ensemble of realities. It offers a calm, rational explanation for the apparent precision of our cosmic home, suggesting a universe that is not necessarily designed, but rather one that explores all possibilities, and we are simply a fortunate outcome of that boundless exploration. The true, real size of the universe, therefore, extends far beyond any measurable distance, even beyond the 46.5 billion light-years of our observable horizon. It encompasses these theoretical realms of infinite repetition and multiple universes, realms that remain forever beyond our direct empirical grasp. Our understanding of these scales is built not on photographic evidence, but on the intellectual elegance of mathematical consistency and the predictive power of our most fundamental physical theories. We use the language of equations and the logic of inference to paint a picture of a cosmos that is far richer, far more diverse, and far more awe-inspiring than anything our immediate senses could ever convey. The inability to directly observe these realms does not diminish their scientific validity, but rather highlights the sophisticated methodologies required to explore questions at the very edge of human comprehension. Just as a mathematician can understand the properties of higher dimensions without ever physically entering them, so too do cosmologists use the abstract beauty of mathematics to explore the unseen dimensions of our universe and beyond. This reliance on theoretical constructs, while powerful, also underscores the provisional nature of scientific knowledge. Our understanding of the universe's ultimate size and the potential existence of a multiverse is constantly evolving, refined by new data and deeper theoretical insights. What we consider a compelling possibility today might be overturned or drastically reshaped by discoveries tomorrow. Yet this dynamic process is not a source of uncertainty, but of intellectual vitality. It is a testament to the ongoing human endeavor to push the boundaries of knowledge, to constantly question, to explore the unknown with a blend of rigor and imagination. This continuous pursuit, this patient unraveling of cosmic secrets, is itself a deeply calming and profoundly satisfying activity, reminding us that the universe is not a static picture to be merely observed, but a living, breathing mystery to be eternally explored. Every new insight, every refined model adds another brushstroke to the grand masterpiece of cosmic understanding, slowly revealing a picture of reality that is ever more intricate, ever more majestic, and endlessly fascinating. This contemplation of our place within such a vast and dynamic cosmos connects us to something truly immense and eternal. It reminds us that our consciousness, however brief, is a precious lens through which the universe experiences itself, a fleeting yet profound moment of self-awareness in an otherwise silent, sprawling expanse. This expansive thought can quiet the mind, allowing the gentle currents of cosmic wonder to carry you into a serene and tranquil sleep, knowing that you are a part of something truly magnificent and boundlessly intricate, forever connected to the deepest mysteries of space and time. The user wants the 9th main body chapter, Part 9 of the script. The previous chapter, Part 8, concluded with the idea of information inaccessibility beyond the cosmic horizon, the role of cosmic inflation in explaining the flatness and fine-tuning of the universe, and the philosophical implications of our consciousness within such a vast, potentially multiversal reality. This chapter should smoothly continue from there, focusing on new, yet related, concepts. A natural progression would be to delve deeper into the nature of these potential other universes, particularly how their fundamental laws could differ, and what this implies about the ultimate reality or the meta-universe from which they might emerge. I will bring in concepts like string theory's landscape or varying constants. Here's a plan. 1. Transition from the idea of fine-tuning and the anthropic principle to the question of why our laws are the way they are, and if they could be different. Connects to fine-tuning from Part 8. 2. Introduce the concept of varying fundamental constants and physical laws across different universes within a multiverse. This expands on the bubble multiverse idea. 3. Explain the cosmic landscape or string landscape concept from theoretical physics, like string theory. This provides a theoretical framework for how different universes could have different laws. It describes a vast number of possible stable vacuum states, each corresponding to a different set of physical laws. 4. Discuss the implications of such a landscape for the real size of the universe. It's not just spatial extent, but the space of all possible physical realities. 5. Reiterate the unobservability of these different laws, universes, but emphasize their theoretical coherence. 6. Conclude with a personal anchor, connecting this profound contingency of our laws to our sense of wonder and the delicate nature of our existence. I will pay close attention to the character count, 8,000 characters including spaces, and ensure all numbers are written as words. The tone must remain consistent with the established Physic for Sleep style, neutral, non-dramatic elegance with intellectual depth, calming, and contemplative. Constraint, checklist, and confidence score. 1. AI role and mission, yes. 2. channel voice and tone, yes. 3. Unbreakable laws of production, yes. High information density, crystal clarity, unified flow, TTS format with numbers written out. 4. Mandatory script structure, main body chapter, yes. 5. Scriptwriter's arsenal, techniques, yes. Smooth flow, scientific tone, scene building, elegant comparisons, personal anchor. 6. Style calibration, guide, yes. Will adhere strictly to the provided example. 7. Content length, 8,000 characters. This will require careful drafting and adjustment. Confidence score, 5.5, strategizing complete. I will now proceed with generating the response. Our exploration into the observable universe, its accelerating expansion, and the theoretical vistas of infinite cosmic repetitions or distinct bubble universes naturally brings us to a contemplation of the very foundations of reality, the fundamental laws and constants that govern our cosmos. We have touched upon the perplexing fine-tuning of these parameters, such as the enigmatic dark energy, which seems precisely calibrated to allow for the emergence of stars, galaxies, and life itself. This leads us to a truly profound question. Are these laws and constants immutable, universal truths? Or are they merely one specific set of rules among an unimaginable multitude, particular to our own corner of the grand cosmic tapestry? In the realm of modern theoretical physics, particularly within the frameworks of quantum gravity and string theory, the idea has gained significant traction that the fundamental constants and laws we observe in our universe might not be fixed, but rather dynamic, varying from one universe to another within a vast multiverse. Imagine, if you will, a cosmic tuning board adorned with countless dials. Each dial represents a fundamental constant, perhaps the strength of gravity, the charge of an electron, or the mass of a quark. In our universe, these dials are set to specific, highly precise values, allowing for the stable formation of atoms, the gentle fusion of stars, and the complex chemistry necessary for life. But in other, perhaps countless universes, these dials could be set to entirely different positions, leading to realities so alien that they defy our deepest comprehension. This concept finds a theoretical home in what is often referred to as the cosmic landscape, or string theory landscape. String theory, a leading candidate for a unified theory of everything, posits that the fundamental constituents of reality are not point-like particles, but tiny, vibrating strings. The way these strings vibrate and the manner in which extra spatial dimensions might be curled up or compactified determines the effective physical laws and constants of a given universe. The mathematics of string theory suggests that there could be an astronomically vast number of ways for these extra dimensions to compactify, leading to an equally immense number of stable vacuum states. Each of these vacuum states represents a distinct universe, a unique bubble in the cosmic foam, possessing its own particular set of physical laws, its own values for fundamental constants, and its own unique cosmic history. Therefore, the real size of the universe in this profound context transcends mere spatial dimensions. It encompasses not just an infinite expanse of space, but an infinite landscape of possibilities, a meta-universe where every conceivable set of physical laws is actualized in some distant, unreachable corner of existence. Our observable universe, with its familiar laws of gravity, electromagnetism, and nuclear forces, is but one particular valley within this colossal abstract landscape. It is the valley where conditions were serendipitously amenable to our form of life, where the stars could shine for billions of years, where complex molecules could form, and where consciousness could eventually arise to ponder its own origins. The sheer scale of this conceptual landscape is almost unfathomable, suggesting a reality that is not merely boundless in its spatial extent, but also in its fundamental diversity, a continuous exploration of every permutation of physical truth. The implications of such a cosmic landscape are both humbling and deeply inspiring. It implies that the universe we inhabit, with all its intricate beauty and delicate balance, is not necessarily unique or especially favored by some singular cosmic design. Instead, it is one among an immense ensemble, a single blossom in an infinite garden of realities. This perspective offers a serene explanation for the apparent fine-tuning of our universe, as articulated by the anthropic principle. We simply exist in a universe where the conditions allow for our existence. If the laws were different, even slightly, we would not be here to observe them. This doesn't make our universe any less wondrous, but rather situates it within a broader context of cosmic experimentation, a natural consequence of a meta-universe that explores all possibilities. Of course, these ideas remain at the cutting edge of theoretical physics, unconfirmed by direct observation. The sheer inaccessibility of these other potential universes means that empirical evidence is extraordinarily difficult, if not impossible, to obtain. Yet the mathematical consistency and explanatory power of these concepts compel scientists to continue their exploration. They offer elegant solutions to some of the most profound puzzles in cosmology, such as the cosmological constant problem and the horizon problem, by positing a grander, more expansive reality. This intellectual journey into the unseen and the unprovable is a testament to the insatiable human desire to understand, to push the boundaries of knowledge, even when direct evidence is elusive. It reminds us that science is not merely about what we can see, but also about what we can infer with rigorous thought and the elegant tools of mathematics, extending our minds into realms far beyond the reach of our telescopes. And so, as we reflect on these profound ideas, we find a deep, tranquil peace in the understanding that our universe, with its unique set of laws and constants, is part of an unimaginably larger, more diverse reality. This vastness, this boundless ocean of possibilities, is not a cause for anxiety, but for a quiet, expansive wonder. It connects us to a cosmic truth that transcends our individual lives, reminding us that we are integral to a story that is grander and more intricate than any single mind can fully grasp. Our consciousness, however fleeting, in its infinite exploration, comes to know itself. May these thoughts carry you gently into the depths of tranquil sleep, secure in the knowledge, a cosmos of endless wonders, forever unfolding. Contemplation of the cosmic landscape, where fundamental laws and constants might vary across an infinite ensemble of universes, naturally leads us to ponder the very essence of what we call reality. If the rules governing existence are not fixed, but rather contingent upon which corner of the meta-universe we inhabit, then our understanding of what is truly fundamental shifts. It moves from a search for singular universal truths to an appreciation of emergent properties, how complex phenomena, from the intricate dance of galaxies to the delicate spark of consciousness, can arise from a vast array of underlying, simpler principles. This perspective reframes the real size of the universe not merely as a measure of its physical dimensions, but as the boundless potential for diverse forms of reality to manifest. The concept of emergence is central to this understanding. Think of a snowflake. Its intricate six-sided symmetry arises not from a blueprint of a snowflake, but from the simple underlying laws of water molecules, interacting as they freeze. Similarly, the complex order and structure we observe in our universe, from the formation of stars to the intricate chemistry of life, may be emergent properties of a particular set of fundamental laws that happen to coalesce in our specific cosmic bubble. In other universes within the cosmic landscape, different laws might give rise to entirely different forms of order, or perhaps to no stable structures at all. This perspective invites a profound appreciation for the delicate balance that allows our reality to exist. A balance that, while seemingly miraculous, becomes statistically probable within a multiverse that explores all permutations of physical possibility. Its boundless creativity experiments with every conceivable form of existence, and we are but one beautiful, improbable outcome of that grand cosmic exploration. Our human perception, inherently limited by our senses and the specific physical laws of our universe, can only ever grasp a tiny fraction of this potential grand tapestry. We see the universe through a particular lens, shaped by the speed of light, the strength of gravity, and the very nature of matter and energy as they manifest in our reality. The realms beyond our observable horizon, whether they are infinite extensions of our own universe or entirely separate bubble universes, remain forever beyond our direct sensory experience. Yet it is precisely through the abstract beauty of mathematics and the rigorous logic of theoretical physics that we can extend our understanding into these otherwise unreachable domains. These intellectual tools allow us to realities that we may never physically witness and what can only be inferred. This journey of inference, of building models that explain the unseen, the human mind, a quiet, elegant equation at a time. It highlights that the real size of the universe is not just its physical extent, but the vastness of the intellectual space required to even conceive of it. This inherent limitation of direct observation, however, does not diminish the scientific validity of these grand theories. Rather, it underscores scientists can infer the existence of a black hole from its gravitational effects. Even though it cannot be directly seen, so too can cosmologists infer the properties of the larger universe from the subtle imprints left on our observable cosmos. The cosmic microwave background, for instance, with its uniform temperature across vast, causally disconnected regions, provides crucial evidence for the inflationary epoch, which in turn suggests a universe far larger than what we can currently observe. These are not mere speculations, but deeply reasoned, serene acceptance that while we may never fully map every corner of the infinite, the very act of attempting to do so, of pushing the boundaries of our understanding, is a profound and deeply satisfying endeavor, connecting us to the universe's most fundamental truths. The universe, in this expansive view, can be seen as an immense, self-organizing system, constantly exploring the vast landscape of physical possibilities. It is a cosmic computer, if you will, endlessly processing information, manifesting diverse realities, and occasionally giving rise to pockets of consciousness like our own, capable of reflecting upon its own existence. This idea, while metaphorical, offers a powerful lens through which to appreciate the intricate dance of matter, energy, space, and time that has culminated in our present moment. Our very thoughts, our memories, our capacity for wonder are all intricate patterns of information arising from the fundamental processes of this cosmic system. To consider ourselves as an integral part of this grand, information-rich cosmos, rather than as isolated observers, can be profoundly calming. It dissolves the illusion of separation, reminding us that we are deeply interwoven into the fabric of existence, a fleeting yet meaningful expression of the universe's boundless potential. As we conclude this journey into, let these profound reflections bring a sense of tranquility to your mind. May the vastness of the cosmos, with its endless possibilities and its intricate unseen depths, inspire not anxiety, but a deep, peaceful wonder. Remember that you are a part of this magnificent unfolding, a conscious observer within a reality that is far grander than any single measurement can define. Let the gentle currents of these cosmic thoughts carry you into a world of serene dance, and you, in your quiet contemplation, are an eternal part of its beautiful mystery. Our contemplation of the universe's true scale, extending far beyond the observable horizon into realms of infinite repetition and diverse physical laws, leads us to a fascinating reevaluation of the very concepts we use to describe it: space and time. We often perceive them as the immutable stage upon which all cosmic events unfold, a fixed backdrop against which the universe plays out its grand drama. Yet at the most fundamental levels, and particularly when considering the vast, unobservable reaches of existence, our understanding of space and time becomes far more nuanced, even revolutionary, suggesting they might not be as fundamental as they appear. Modern physics, especially general relativity, has already taught us that space and time are not separate, static entities, but are inextricably woven together into a dynamic, four-dimensional fabric known as space-time. This fabric is not merely empty, it can be curved, stretched, and warped by the presence of mass and energy. This curvature is what we perceive as gravity. When we speak of the expansion of the universe, we are speaking of the stretching of this very fabric, carrying galaxies apart. This dynamic nature implies that the size of the universe is not a static measurement, but an evolving quantity, deeply intertwined with its history and its future. But what if this space-time itself is not the most fundamental layer of reality? What if it, too, is an emergent phenomenon arising from something even deeper? The idea of emergent space-time is a profound one, hinting that the dimensions we perceive, the three spatial dimensions and the single dimension of time, might not be inherent, foundational components of the universe. Instead, they could arise from more fundamental, microscopic constituents or principles, much like the smooth, continuous surface of a fluid emerges from the collective behavior of countless individual molecules. Theories attempting to unify general relativity with quantum mechanics, such as string theory or loop quantum gravity, often explore this very possibility. In some of these models, space-time as we know it dissolves at the incredibly tiny Planck scale, the smallest conceivable unit of length, into a frothing quantum foam, or it merges from the interactions of fundamental strings or loops. If space-time is indeed emergent, then the question of the real size of the universe takes on an entirely new dimension. It is no longer just about measuring the physical extent of space, but about understanding the underlying structure from which space and time themselves originate. The unobservable horizon, then, is not merely a boundary of light travel, but a glimpse into the limitations of our space-time dependent perception. Beyond that horizon, or beneath the surface of our familiar space-time, could lie the true, more fundamental reality. A reality where the very concepts of distance and duration might be entirely different, or perhaps even meaningless, in the way we usually define them. This perspective encourages a deep, meditative surrender to the unknown, allowing our minds to float beyond the familiar anchors of our everyday world and embrace a more profound, almost dreamlike understanding of existence. Consider the holographic principle, which we briefly touched upon previously. This radical idea, stemming from the study of black holes and quantum gravity, suggests that all the information contained within a three-dimensional volume of space can be encoded on its two-dimensional boundary. If this principle applies to the universe as a whole, it implies that our three-dimensional reality, with its vast spatial extent and flowing time, could be a kind of projection or an emergent property of information residing on a distant, two-dimensional cosmic surface. In such a scenario, the real size of the universe would not be its apparent volume, but the information capacity of this boundary, a measure of its underlying complexity, rather than its physical expanse. This is a truly mind-bending thought, suggesting that the very solidity and dimensionality of our world might be a grand illusion, a beautifully rendered cosmic hologram. Such concepts, while highly speculative, illuminate the depths of the universe's mysteries and the limits of our intuitive understanding. They invite us to reconsider what real means and to embrace a more expansive, yet tranquil, view of existence. The unobservable universe, then, is not just a spatial extension, but a realm where the very rules of reality might be subtly or even dramatically different from our immediate experience. It is a testament to the universe's boundless creativity, its capacity to manifest reality in forms that stretch the very limits of our imagination. And in contemplating these profound depths, these quiet, unreachable domains where space and time might emerge from something deeper, this journey into the nature of emergent space-time and the potential for reality to be a projection from deeper, more fundamental structures, offers a unique opportunity for tranquil reflection. Our consciousness, arising within this emergent reality, is itself a remarkable phenomenon, capable of pondering these very questions, of seeking to understand the underlying code of existence. We are, in a profound sense, the universe awakening to its own intricate design, a fleeting yet precious manifestation of its boundless potential. reminds us of our deep interconnectedness with all of existence, a serene thought that can quiet the mind and allow a world of peaceful, restorative sleep. A cosmos where the very fabric of reality is an intricate, unfolding mystery, forever connected to the deepest truths of space and time. Our contemplation of emergent space-time and the holographic principle has led us to the very edge of our understanding, where the familiar anchors of reality seem to dissolve into deeper, more abstract truths. The universe's real size then transcends mere physical measurement, encompassing a conceptual vastness that challenges our deepest intuitions. This brings us to a crucial realization. Our everyday perception of space and time, of solid objects and linear progression, is merely a surface-level experience, a convenient simplification that allows our consciousness to navigate a profoundly intricate and multi-layered reality. To truly grasp the scale beyond the observable horizon, we must journey beyond the limits of ordinary thought, into realms where the very definition of existence is subject to re-examination. The human mind, a marvelous product of billions of years of cosmic evolution, is exquisitely adapted to perceive and interact with a specific slice of reality. Our senses are tuned to a narrow band of electromagnetic radiation. Our experience of time is linear, and our understanding of space is intrinsically three-dimensional. Yet, the theories we have explored, from cosmic inflation generating a vast, unobservable universe, to the string landscape positing countless realities with different fundamental laws, and even the holographic principle suggesting an emergent space-time, all demand that we stretch our cognitive frameworks far beyond these biological limitations. This is the profound power of physics, to allow us to conceptualize, to mathematically model, and to contemplate realities that lie entirely outside the scope of our direct experience. It is a testament to our intellectual curiosity, a quiet insistence on pushing the boundaries of what is knowable, even when the answers reside in realms we can never physically touch. In this grand intellectual pursuit, the very notion of what is fundamental undergoes a transformation. If space-time itself is emergent, arising from a deeper quantum reality, then the search for the universe's real size becomes a quest for the underlying code, the fundamental information, or the most elemental constituents from which all of existence, including space and time, ultimately springs. This echoes the ancient philosophical quest for a unified theory, a single elegant principle that can explain all phenomena. Modern physics, in its most ambitious forms, continues this quest, seeking a theory of everything that can reconcile the seemingly disparate realms of the very large, governed by general relativity, and the very small, governed by quantum mechanics. Such a theory, if ever fully realized, would not only describe the laws of our universe, but might also provide a coherent framework for understanding the entire cosmic landscape, the vast ensemble of potential realities. It would, in essence, reveal the true, ultimate size of all that is possible. The implications for our understanding of consciousness within such a boundless and potentially emergent reality are particularly profound. If our universe is one of many, and its laws are but one setting on a cosmic dial, then our awareness, our capacity for thought and wonder is a precious and perhaps rare phenomenon. It is the universe, in a fleeting yet meaningful moment, becoming aware of its own intricate design, its own boundless potential. Our individual consciousness, then, is not merely a localized event within a vast, indifferent cosmos. It is an intrinsic part of the universe's self-reflection, a delicate and intricate pattern woven into the very fabric of emergent reality. This perspective fosters a deep, calm sense of belonging, reminding us that we are not separate from the cosmic dance, but an active participant, a unique lens through which the universe experiences and contemplates itself. Embracing the profound unknown, the vastness beyond our observable horizon, the possibility of emergent realities, and the contingent nature of our own physical laws can be a deeply calming experience. It dissolves the illusion of absolute certainty, replacing it with a serene acceptance of mystery and an expansive appreciation for the universe's inexhaustible creativity. The true, real size of the universe lies not in a fixed number, but in its infinite capacity for surprise, its endless potential for new forms of existence, and its continuous invitation to intellectual exploration. It is a reminder that the quest for knowledge is not about reaching an end, but about embracing the journey, allowing our minds to expand with every new insight, every theoretical leap, every quiet moment of contemplation. This continuous unfolding, this eternal dance of discovery and wonder, connects us to something truly immense and profoundly beautiful. And so, as you drift deeper into tranquility, carry with you this sense of expansive wonder, world of peaceful, restorative. As our minds gently retreat from the intricate dance of emergent space-time and the profound implications of a potentially holographic cosmos, we arrive at a tranquil understanding. The real size of the universe transcends any simple measurement. It is not merely a number of light years, but a boundless tapestry of possibilities stretching infinitely in space, encompassing an untold number of realities with varying laws and unfolding across a dynamic, evolving expanse of time. Our observable horizon, while vast, is but a fleeting glimpse into this immeasurable whole, a luminous bubble within a grander, largely unseen ocean of existence. May these deep thoughts about the true, unfathomable size of the universe carry you into a world of tranquil sleep. Remember that the cosmos, in all its intricate majesty and silent grandeur, is an amazing, self-reflecting entity, and you, with your capacity for wonder and understanding, are an integral part of its enduring story. Fall asleep with this feeling of serenity, knowing that your consciousness and the boundless potential that lies just beyond the reach of our current perception. Good night.